All right. Hopefully you guys can hear me. We have returned. All right. Why is my model? Oh, there it is. Okay. Let me get chat ups because I forgot to do that. I can. Okay. Hi, Tsuni. Hi, Astral. If you've made it back yet, hi, Stumpy. Hello, everyone. Why is chat not sideways? Okay. Good. All right. I have returned. And it's time. Whoops. All right. It's time to continue. Shoot. What the heck? Everything's going wrong now. Oh no. Where's the I'm reading. I have chat off my phone to read, which is gonna die soon. Why do I have chat off my phone to read when I can just do that? Let's do. Can I do a switcheroony here? How good are my switcheroony skills? Okay. We should be back. I think. Whoops. I think we're back, and now I can read chat without interrupting anything. Wait, what? It switched it back? What the heck? What's the heck and heck? Oh wait, no. That's right. My model is where my model is. Here. You are model. The screen is this. Okay, we're back. We're officially back. All right. So, where we left off, we had just finished the lanthanides, the wonderful lanthanides, and now, I guess, let's do the main group. So these are the transition metals, although we kind of already did scandium and yttrium, but that's okay. That is not a problem. All right, and for some reason my computer's being slower, but we're just going to ignore that and pretend that's not happening. Electrons aren't real. Computers aren't real. Nothing is real. It doesn't matter. All right. So, next up, we have titanium. Titanium is very cool in many ways. You probably know it for being strong and stuff. But titanium is incredibly useful in the production of certain plastics. So here's a little, I can actually really draw this out. So one of the things that I was trying to do, which turns out to be way too hard, but like that I was thinking of doing as a project, is making a plastic called polypropylene. Where's polypropylene? There's polypropylene, which kind of is basically the propene molecule looks like this. And so what you can do is if you have multiple propene molecules, you can chain them together to make a molecule that looks a little bit like this. It's kind of, I'm not drawing this exactly right, and actually that should be, is it that or that? I think it's that. I don't know, whatever. The point is, it's a very common thing you want to do, where you want to basically merge these double bonds together, and it's very useful in the production of plastics, but also in all kinds of other stuff. And it turns out the catalyst that we use to do this, because this is a reaction that could happen. So like here's the energy of the product or of the reactants, and here's the energy of the products. It's possible, but it has this huge barrier, right? So this is the polymerization of something like propylene, right? That's what these are. These are propylene. Basically doesn't happen, at all. So you need a catalyst, which will form some kind of intermediate. So we'll go here and we'll have some kind of, here's propene, and then we'll have the catalyst, and this is all sort of form one chunk, which will have a much lower, whoops, I'm drawing this so terribly, which will have a much, much lower, much smoother energy. And it turns out the catalysts that's used for this are almost always titanium-based. So it's usually titanium chloride with either 4 chlorines or 3 chlorines. Now wait, how is that possible? How can you have 4 chlorines or 3 chlorines? I mentioned briefly oxidation state when I talked about the lanthanides. So one of the reasons that europium is different than the other lanthanides is most of the lanthanides can only bond using 3 electrons. So like samarium, or actually samarium is not quite a good example. Yeah, but let's say let's pick one. Gadolinium, right? Gadolinium can, for the most part, only bind to 3 different things. So this is gadolinium 3+, because it's in the 3+ oxidation state. And europium is unique because you can have europium 3+, but also 2+. This 2+, what makes europium weird and thus changes its crustal abundance, is the fact that the 2+ state is relatively accessible. In other cases, you can make samarium 2+. Right? Samarium, actually one of the cool things about samarium I mentioned is samarium 2 iodide, so that's samarium bonded to 2 iodines, is a very useful reagent for doing organic chemistry, which is kind of weird because organic chemistry is all about manipulating carbons, and there's no carbon here. This is just a weird lanthanide compound, but it works. It's a very useful reagent. But again, this is samarium in its 2+ oxidation state, which is possible, but not super common and kind of a pain in the ass to get. Europium's not like that. The main group elements, these are, and a lot of the transition metals are even less like that. So they have many, many different oxidation states a lot of the time, and it's not too hard to go between them. Titanium, so there's you can have titanium 3 chloride, and you can also have titanium 4 chloride. Both of these are compounds that are just things. Titanium has a lot of interesting chemistry, though. It's obviously useful for metallurgy stuff, but it's useful for lots of other things, too. I mentioned electrides earlier. It turns out you can make a weird phase of titanium oxide, which is an electride. So I believe is this the 0.6? No, this is, yeah, so you have 2 electrons as part of the compound of, titanium 2 oxide. Oh, I didn't even talk about the oxide. So this is like a weird, cursed version of titanium oxide. But the most common titanium oxide is TiO2. So this is titanium, and so this is titanium oxide, and titanium oxide is used for a bunch of stuff. It's used a lot of times as a white pigment because it's very white, so it's a very common white pigment. It's also used for some cool solar panel stuff, and for doing photochemical reactions, I think. You can use titanium dioxide nanoparticles. It's a pretty versatile material. It's quite cool. So titanium, it's not the coolest thing, but it has a lot of fun stuff going for it. And so if I can dig around through all of the elements here, it's the first one. Of course, it's the first one. We've got our friend titanium, and I don't know. I think it goes in C tier. It's cool, but not it's not crazy, but it's cool. All right. Next up, we have vanadium. Vanadium is crazy and cool. So vanadium also forms different oxides. One of the most notable ones is, so there's different oxides actually here. I can just use the power of the internet. Vanadium oxides. There's V2O5 is the toxic one. Yep. Which you can see, it's this very beautiful orange powder, and it's also very toxic and dangerous. So 4 out of 4 is the highest health hazard rating. It's very weird to see. It's incredibly toxic, but it's not flammable at all, and it's not reactive at all. So yeah. And then if you ever see this symbol, this is it's toxic to aquatic life. But yeah. So this vanadium oxide is very toxic. A lot of transition metals, the metal item itself is totally fine, right? Chromium metal is a part of forks that you eat with. In a significant amount too, not a trace amount. But chromium in compounds, I'm skipping ahead, but chromium in compounds are often extremely toxic. So you have this contrast a lot of times with transition metals, but the metal by itself is chill. But the metal as part of a compound is very not chill. But yeah, there's other vanadium oxides too. They're all generally pretty toxic. And one of the cool things about vanadium is that I mentioned, a lot of these have different, very accessible, many oxidation states, and it's very easy to access a lot of those oxidation states. Vanadium has, I believe it's like V5 plus, V4 plus, V3 plus, and V2 plus are all pretty easily accessible. It's ridiculous. There's even it's like a common experiment in like undergrad, like undergrad chem labs, where you start with vanadium, like vanadium 5 plus, and then you reduce it, and you can see a color change as you go through all of these. Because that's one of the coolest parts about transition metal chemistry is I mentioned titanium. Oops, I mentioned titanium, like titanium 4 chloride. Actually, titanium 3 chloride. They all look pretty cool too. So here's titanium 4 chloride. Oh, it just looks chill. Titanium 3 chloride is this beautiful purple color. Frick. So the different oxidation states have different colors, and a lot of the colors are really, really pretty. So transition metal chemistry is quite cool in that way. But yeah, so you start with, it's a common experiment in like undergrad stuff to start with 5 plus vanadium, and then you can reduce it and you can see a color change as you go from one oxidation state to the other. But this is also useful for another reason, which is batteries. So one of the things you can do is we'll make a little barrier here, and we'll have a little box, and on one side we can put in vanadium 5 plus, and take out vanadium 4 plus. I think I might not be getting the exact details right, but on the other side we can put in vanadium 2 plus and get out vanadium 3 plus. So how is this happening? Well, we have we have electrons moving throughout the system. I'm explaining this horribly, but the point is that because there's 4 different fairly easily accessible oxidation states of vanadium, you can make a battery where the vanadium, where it's the only actual, like the cathode of the battery is vanadium. The anode of the battery is vanadium. And because you have these 4, unique states, but they're all the same element, you can actually make these like tanks of liquid. So you can make what they're called flow batteries. And there's a lot of startups with too much money playing with them, but it's still a really cool idea. So you can connect these to tanks and basically flow your anode and cathode around. So the way normal batteries work, you have here's your anode on one side, you have your electrolyte is some kind of, something, sometimes it's a liquid, sometimes it's something else, and then you have your cathode on the other side. In a flow battery, it's like the opposite, like the intermediate layer is solid, and then you have a liquid anode. It's usually called an anolyte, and instead of a cathode, it's a catholyte. So it's a really, really cool concept. And flow batteries are awesome. Vanadium flow batteries. It's just you can just use vanadium. Everything is vanadium. It's everywhere you look. It's vanadium, all vanadium. It's really fun. So for that reason, and the fact that it's cool, and also it's just a fun name too. I don't know. It's V. Vanadium gets B. Vanadium is B. Oh, hi Stumpy. So this is our terrible drawing of a vanadium flow battery. All right, back to the next one, chromium. So I teased a little bit chromium. Chromium is present in stainless steel. So if you have there's a great video by the channel Amateur Chemistry, starting with just stainless steel forks and going from the pure chromium metal as part of an alloy to chromium to I believe it's hexavalent chromium. So, oxidation states, this is chromium in its 6 plus oxidation state. And this version of chromium is very, very toxic. So chromium, is huge toxicity issue. Again, the metal is not fine. It's chromium in its 6 plus oxidation state that's super toxic. But it does do some cool stuff, and I don't know, it's fine. D tier. Actually, the forks thing was pretty cool. The video of turning forks into chromium might be pushing it up a little bit, but I don't know. I've generally been putting more toxic stuff down at the bottom unless it has a good excuse for it. So I think you're going there. Next up is manganese. Manganese is quite a fun. It's a fun little thing. So one of the most common chemicals containing manganese is well, there's two kind of. Manganese dioxide is common in batteries, so it's this black powder that you can find inside a lot of different batteries because yay batteries. The other one is potassium permanganate, which is very common as a reagent, and it has this beautiful purple color, which hopefully there will be a picture of. Well, the crystals will look blacker, but that's if you have it in solution, it's there we go. There's our friend KMNO4. So it's this beautiful purple color. It's really cool, and one of the fun things that potassium permanganate can do is catalyze the decomposition of hydrogen peroxide. So again, that sounds fancy, but you probably know you get hydrogen peroxide, which is H2O2, from, or we'll have 2 moles of that, so we'll have 2 H2O2s from, you can just get this, as a solution in water from like the pharmacy and stuff. And it turns out that very, very slowly, it decomposes into hydrogen with oxygen, which is water. I don't know why I said it like that. But yeah, so it decomposes into water and oxygen. And this happens normally. It happens very slowly, but there are things that can make it go faster. For example, hydrogen peroxide in the store is usually stored in like black, not see-through containers. And that's because like sunlight and ultraviolet light, and even just light in general, like visible light in general, can trigger, this decomposition happening even faster. But it turns out that potassium permanganate can act as a catalyst to make this go really fast. And it makes it go so fast that it was actually used in like rockets, not as the actual rocket engine, but to produce like a huge amount of steam, which could drive. So you have this it was this ridiculous pathway where you have, here's your hydrogen peroxide. So you have potassium permanganate, right? Here's your KMNO4. I'm drawing this so badly, but whatever. And it catalyzes the decomposition of hydrogen peroxide, which produces a huge amount of steam. And that steam is used to drive your pumps, which like pump fuel and stuff into your rocket really fast so you can have your crazy rocket. I don't know if it was the V2, but it was like that era of, I think it wasn't the V2 actually. But the point is that this decomposition produces steam so fast that it's been used to drive like rocket level stuff, not the actual rocket engine itself, but like you want to turn on a pump really really fast for whatever reason, you can use this fun little catalyzed reaction. So manganese is pretty cool. Different oxidation states are fun. I believe it's used in some pigments also. Actually, manganese is the first of, there's speaking of pigments, it turns out that we haven't discovered like a new pigment in a long time. Pigments like themselves, there are compounds that are colored, but compounds that are actually going to act as pigments are really quite rare. Yummy hexavalent chromium, me when titrating. VTuber, actually that's so good. I didn't even realize that. Yeah, vanadium for VTuber. Actually, you know what? It's going in S tier. It's going in not S tier, but we'll put it in A tier. I think it can go in A tier. V for VTuber. It's just perfect. It's perfect. And yes, the hexavalent chromium is absolutely delicious. But yeah, manganese is pretty cool. What was I was going? Oh, pigments. Yeah. So we haven't discovered that many pigments for a very long time. But in like, I think it was the early 2000s, we discovered that some researchers discovered that if you mix yttrium, indium, again, it's top tier freaking element yttrium. Oh, I'm so close to putting yttrium in S tier. Okay, here's the deal. If one other cool thing comes up that I haven't already talked about that uses yttrium, it's going in S tier. That's the deal. That's going to be the deal. All right. But if you mix yttrium, indium, and manganese, you get this. This is a new synthetic blue pigment that looks really cool. So they gave it the very creative name of Yinmin blue. Hopefully, I'm never remembering this right. Yeah. Yttrium, indium, and manganese, and it's this blue pigment, and it's crazy. It's the first discovery of a pigment in a very very long time, and it's really cool. So that's another fun manganese thing. Manganese has played a role in many different pigments. Obviously, potassium permanganate is quite a brilliant purple color. It's fun, and my computer has decided to die on me again, but that's okay. It came back to life. Manganese is all right. It's pretty good. I think we can do. I feel like there should be a C+ tier and a C- tier or something, but I don't know. Manganese, where is it? There we go. Let's do. I think it's C tier. It's all right. It's all right. It doesn't quite It's fine. Iron. Now we get to iron. Iron, probably the coolest thing about iron is, there's so many cool things about iron. One of the coolest things about iron is that it marks the point. So up until iron, it is more beneficial to fuse nuclei. So the idea is that if you put together smaller nuclei, right, here's your nuclei, and you put, you make big nuclei. Wow. This is right. If you do nuclear fusion, and you can also do the reverse is nuclear fission when you split them out. And before you get to iron, this is favorable, right? It's favorable. It's energetically favorable to fuse nuclei, and it's not energetically favorable to split nuclei. You gain energy when doing this, you lose energy when doing that. After you get to iron, though, and iron is included in this, it flips. It's suddenly more energetically favorable to have the nuclei be separate. And so iron is quite literally why stars die, because the stars are fusing nuclei, and eventually when you hit to iron, it becomes no longer energetically favorable, and the star dies. So that's one of the cool things about iron. It's obviously used a lot for its magnetic properties. I believe one of the first organometallic compounds is also based off of iron. So the idea behind organometallics is you have organic chemistry, which is on one side, right, which is just carbon, and lots of carbon. We love carbon. Organic chemistry is all about that carbon, and inorganic chemistry, which is everything else, right? And so people were wondering, well, obviously we've had bonds where here's carbon bonded to an oxygen, and here's carbon bonded to a hydrogen, and here's carbon bonded to a nitrogen or whatever, and you can do all kinds of crazy weird stuff bonding carbon and nitrogen together. But what if you bonded carbon to a metal? So this is the idea of organometallic chemistry, is can we make a molecule that contains both organic parts and a metal, hence the name organometallics. And I believe it was the first organometallic compound ever made, or I'm totally not, and I'm going to look really stupid in front of all of you, but it's called ferrocene, and it's like a sandwich. It's so cool. Yeah, so it's a context consisting of two cyclopentadiene rings submitted around a central carbon atom. So you can see this is not a normal bond to. What we have here is, so cyclopentadiene is basically just a pentagon of carbon, and then you have two double bonds. But because of chemistry, these bonds are delocalized and are sort of spread out through the entire ring. That's aromaticity. I might talk about that more later. It's a very cool and important concept, but for now, what matters is that because of this aromaticity, this ring is quite stabilized. But it also, sort of implies delocalization. And so this right here is our, cyclopentadiene ring. And what you can do is you can have iron sandwiched between two of these. And this the iron will actually bond to both of these rings. And this gives you ferrocene. And there's been, since ferrocene was discovered, there's been a bunch of people have done analogs of this for all kinds of different metals. It kind of depends too on the way the metal. Oh no, my computer is dead again. There we go. It kind of depends on the metal which what kind of things you can do with this. For example, here you can notice the iron is bonded to two things. If you wanted to do this with titanium, you kind of can. You can have, here's your cyclopentadiene ring here, but it has to be bonded to four things. So here's your cyclopentadiene, here's your cyclopentadiene, and then you have to bond it to two other things. You could either have this here, or you could put something else here. It has to be generally the way this works is bonded to four things. And actually, I mentioned catalysts for using different catalysts for propylene polymerization, right? So when you want to make plastic out of these propene monomers, one of the ways that you do this is with basically the same thing I just drew, but I'm going to have to draw it again because I deleted it. And so you get to witness my miserable drawing skills. Doot, 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 doot. And then I don't remember what goes here. I think it might just be hydrogen. Whatever, I'll put question marks there. But if you make this sort of, this similar thing that titanium forms, where you have, it's kind of like ferrocene, but you have these extra groups because of the oxidation state. This actually also works as a catalyst for that reaction. But anyway, that's a huge sidetrack. We're not talking about making plastics anymore. We're talking about ferrocene. Ferrocene's so cool, and it sparked this whole it sparked this whole area really, because it was like, hey, we can do this. We actually do this thing. It's really quite fun. And yeah, I can probably find, so like the thing that I showed before, that was like a zircanosine base, but of course zircanosine? It was chlorine, that's what it is. It's not hydrogen it's bonded to, it's chlorine. Yeah, so you can see it looks a little bit like that. And this is used as a precursor. Because one of the cool things about this approach, right, ferrocene is really cool from like a theoretical perspective, but you can't really connect anything to it, right? You can't connect anything. Connecting anything here doesn't really work, or at least it's very hard. And you've already used up the slots on the iron. But if you have something like this, you can connect other groups in the place of the chlorines here. So yeah, metallocenes, which is this kind of general structure, are very cool. Ferrocene is the OG metallocene. It's quite fun. And yeah, oh wow, it has a big list of them here. Oh yeah, uranocene. Oh boy, uranium does. What is this? That's not cyclopentadiene. There's 7 of them. I think there's 7, if I count right. Wait, no, it's 8. Yeah, it's cyclooctatriene. Yeah. What is this? What is this cursed madness? We're not to uranium yet, but we'll get there. Is our OG vanadium? Yeah, vanadium does something similar to iron. Yeah, it's pretty cool. But anyway, ferrocene was very important, not practically, but in terms of showing that organic metallic chemistry could be a thing, and iron kills stars, and it's just awesome. It's just freaking awesome. Best element is carbon. It's what graphene was made of. I mean, we'll get to carbon. Carbon is definitely up there. Pretty sure heme was made first. Oh, ferrocene catalysts are used for polyethylene. I didn't know that, actually. I mean, a lot of, I will say, like, one of the main uses of organometallics is catalysis. So I didn't know that. That's cool. Pretty sure heme was made first, though. Let's see. Was that technically the first organometallic compound? I mean, it's a little different because it's a coordination complex, and you can make coordination complexes a lot easier than you can make true organometallic compounds. That's the thing. I should just, we're checking this live. Yeah, I wouldn't really consider it a organometallic compound. We can talk a little bit more about coordination complex in a second, though. Its unusual stability for blah, 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 blah. Yeah, there's a bunch of analogs. I talked about all this. I know my ferrocene. Oh well, I don't know whether. I mean, I'm pretty sure this was first, but I think this is a coordination complex and not an organometallic, and I wouldn't class those as the same thing. Biblically accurate. Yeah, I know these drawings are hopefully great. Okay, well, we need to rank iron, and iron is definitely S tier. Come on. Cobalt. Oh, Cobalt's awesome. Cobalt is a great element. It's also, we can talk a little bit more about nuclear stuff. So I mentioned cesium-137 is common as like a, industrial radiographic, like, radioactive source. Cobalt-60 is another common one that has also been involved, unfortunately, in accidents that were not actually that bad on the scale of things, but people think are really scary and stuff. So cobalt-60 is isotope that decays. It's very radioactive. There's been some problems with it finding its way into steel because it is cobalt, right? You have to remember the isotopes. You can't unless you have a Geiger counter, you can't just see them. So there's problems when cobalt-60 containing materials are scrapped and mixed with steel, and now you have your cobalt-60 emission, which is very, very bad. But cobalt does all kinds of cool stuff. Cobalt is a great element for forming coordination complexes, which is the other thing I was talking about, something like heme. So organometallic chemistry, the idea is you want to form as basically normal bonds between a carbon and iron or whatever. Organometallic chemistry is that's organometallic chemistry. Fuck, I can't talk. Coordination complexes are a sort of a special type of compound where what you have is you have some central metal atom, and then you have other things that are called ligands. So you basically have other things bonded to it. Or let's say these are, I don't actually know too many of these. You can have, for example, aqua ligands, where it's like water. You can have, I think you can have nitrosyl ligands, but I forget the exact expression for it. I don't know that much about coordination chemistry. Other than that, it's very cool. And the other thing is that these are not normal bonds. These are what you would call dative bonds, because instead of a normal bond where you have like a normal covalent bond, right, is you're sharing one electron, where here's like, here's the first thing, here's the second thing, and there's overlap between the orbitals. Dative bonds are where it's a 2 electron bond. So they're all going to A. So that's why you have this arrow sort of notation. But coordination complexes, you can have they basically let you like click these things together like Legos, because you have different ligands that do different things. And even if they would normally not be, you can't just have them in solution together, maybe they would react or something. You can form a coordination complex where you want to combine all these crazy ideas you have and put whatever you want, and you can make them ligands of coordination complex. It's a very, very cool thing you can do. Do Grignard's reagents, gotta go as it's like 3:30 a.m. here. Oh yeah, feel free to go based on time. Reagents. Are Grignard reagents considered earlier organometallic stuff? Well, Grignard reagents are, for those of you who don't know, and my computer's dying again. Those are organomagnesium compounds. Organometallics generally refers to like transition metals. You wouldn't count magnesium. It's a very useful. I can talk a little bit about Grignard reagents though, because I think I put magnesium quite high. Yeah, magnesium is in B tier. One of the cool things you can do with magnesium is, let's say you have a compound here where you have a bunch of stuff. I don't know. Maybe it looks like this, and we'll make it a secondary alcohol. Whatever. And you have a halogen. Let's say a bromine group here. What you can do is do a little switcheroo where you can sneak a magnesium atom in here. And then, frick, this is the Grignard reaction. This is now your Grignard reagent, which is kind of a pain because it's like water sensitive and stuff. But what you could do is you can react to this with other organic compounds. And what's really important, the gist of this, I'm not going to go in a full lesson and explain Grignard reagents. The gist of this is that it lets you form new carbon-carbon bonds. So you can take these two things and combine them together, which in organic chemistry is like very, very useful. You want to be able to, you don't want to have to build everything one bit at a time and put a thing there and then put a thing there and put a thing there. You want to be able to, build part of the molecule, and then connect them together. So Grignard reagents are very useful. I wouldn't consider them organometallics because generally you're referring to like transition metals. All right. Let me make sure there aren't. Or even Prussian blue. Yeah, Prussian blue is a coordination complex. I think. Let me make sure that is. It's just sodium ferrocyanate, right? Or not sodium ferrocyanate. It's iron. Yeah. Yep. I believe it is a coordination complex. Doesn't actually say that here. Is it not a coordination complex? What? Am I getting bamboozled live on stream? I really thought it was a coordination complex. Oh, due to coordination to sign. Yeah, it's a coordination complex. They just didn't draw the dative bonds because they wanted to be able to show they wanted to show like this is going out, which ones are going out of the page and into the page and stuff. Yeah, that's okay. Yes. I believe it is a coordination complex. Anyway, coordination complexes are cool. Cobalt is quite good at forming them. And one of the last really cool things about coordination chemistry is that as you do, generally, I mentioned these solutions often have a strong color. The color will often change because as you add different ligands, because those ligands will, handle differently the electrons that are actually connected to the atom, and it's those like that electron behavior that determines color. So the gist of it is that you can actually see like whether you're putting on different ligands by a color change. It's just really, really fun. Coordination chemistry was really quite cool. Cobalt's a great element. Cobalt 60 is fun. It's obviously used, has metallurgical purposes too. Metallurgy, I mentioned samarium cobalt magnets being like the second strongest magnets, but they are much more heat resistant than neodymium ones, which is quite cool. Cobalt's a pretty great element. I'll put it in B tier for now. All right, let me get this. Nickel's cool. for nickel, I want to tell a little story, which again goes back to batteries. So Toyota sold this car called the RAV4 EV. There we go. The RAV4 EV. I know half of this is in Wikipedia, but like, it's fine. I'm telling a story. There we go. We can go to Toyota's webpage. Look, it's the RAV4 EV. It's an electric car, and it's an electric car that was discontinued. They made it in 2014. This is a long time ago. There were not very many electric cars and not very many big electric cars in 2014. This is a little unusual. But the RAV4 EV was, I should make sure I say the dates right. The first generation was leased from 1997 to 2003, and eventually production ended in 2014. So production of the second generation was limited during a 3-year run. Basically, where's the freaking dates? Whatever. The point is that the second generation lasted from like 2012 to 2014. They had like 2 years. There's barely any of these cars out on the road. But what's even crazier is that the cars that are out on the road are still there. If you know anything about electrical vehicles, you'll know that the batteries that we use, which are lithium-ion, lithium batteries, these batteries degrade over time. They degrade over time. It's not that badly, but it means that it's eventually the battery is going to degrade to the point where it's not usable anymore. But lithium has the advantage of being having huge energy density. Right? I'll just put E dense. There we go. What the Toyota RAV4 EV did not have a normal lithium-ion battery, because those weren't really a thing yet. It had a nickel metal hydride battery. Now, the idea of using nickel in batteries isn't new. You may be familiar with nickel cadmium batteries, which are basically just toxic. I don't know. I forget exactly what the advantage of using them is. They're used in like hobby stuff, I think, a lot. Cadmium is really, really toxic, though. So that part of it isn't great. But anyway, they were using nickel metal. The Toyota and stuff were using nickel metal hydride batteries, which is still right. One of the things, though, so you can see they have about half the energy density of lithium-ion batteries, and it's similar to nickel cadmium, right? So it's just chill. Toyota's using their nickel metal hydride batteries. Nickel metal hydride batteries, I'll just represent them as nickel for now. They are not as energy dense, right? They're not as energy dense as lithium-ion batteries, but they also don't degrade, like barely at all in comparison. They last for ages. They have a bunch of other weird behavior, like they had to warm up. If you hadn't driven in a while, your battery would have like a quarter of the normal percentage, and then after you drove it for a while, it would be back to normal. They had some weird behavior. But what's interesting, why I'm telling this whole story about them is what happened to the patent for our little nickel metal hydride batteries. Zeiss's Schultz should be earlier too. As soon as you say something like it's the first X, someone's going to find an earlier one. Air stable yellow. It's a coordination complex. See? These are coordination complexes. So the historical importance in organometallic chemistry. Like it's a coordination complex. But ferrocene was not, and it's different. Okay, it's different. Yes, there were many coordination complexes discovered and characterized before that. Also, this is really cool. If you hadn't noticed, what? All right. Anyway, back to the story of our friends' lithium metal batteries. You can see, there's a little article about it, because what happened was the patent for these nickel metal hydride batteries. Where's the patent? So there's the patent for these nickel metal hydride batteries was transferred at some point to. Okay, I want to make sure I get this right. I don't want to lie about legal stuff. That would be very sad. It was GM, right? It was GM? Yeah, it was GM. And it was underneath like GM Avionics or something. It was underneath GM. So GM had acquired the patent for it. And then, what's this? In October 2000, the oil company Texaco announced the purchase of General Motors' share in their avionics division. So we have nickel metal hydride patents, which are owned by, GM Ovionics, which are owned by GM, except no, they're not now, because they were transferred from Toyota. Now they're owned by Texaco, which is, I believe, owned by Chevron. It'll probably say that there. Texaco was then acquired by the rival Chevron. And so now the patent for electric vehicle batteries is in the hands of an oil company, and they do not much like electric vehicles. So they basically were able to use their ownership over this patent. That's why the RAV4 EV was like only made for like, the second one was only made for like 2 years, is because you were able to use this patent to tell Toyota, don't make electric vehicles. You can't do that. We were not letting you do that, because of course they're going to do that. They're a freaking oil company. So that's my little story about nickel. Nickel is again, it's used for battery stuff. It's also, I believe it's quite expensive, and it's used for like making metals and stuff too. Lots of nickel compounds are quite useful and have interesting semiconducting properties, so they're used for a lot of weird material science stuff that I love. And a lot of them, I think there's some photochemistry stuff too you can do with nickel. However, a lot of nickel compounds are really, really bad for aquatic life. They're really toxic to aquatic life, which is a bit of a problem. But there's something else that I keep forgetting, and I don't know what it is. There's something about nickel. Oh well, nickel's pretty cool. There's nickel compounds and photo something, and I don't know. I'll remember it later. For now, nickel's pretty cool. It goes in B tier. It goes with cobalt. All right, copper. It's copper time. Copper is great. Copper is great, but it's also horrible. So copper it's obviously used to make wires and stuff, and as an electronics nerd, I definitely appreciate copper. Copper is great. It's S tier. There is one thing that makes me hate copper though, which is copper. There's copper 1, right? So I mentioned oxidation states. All right, there's copper 1, so this isn't just another way to write oxidation states because chemists can never agree on anything. And there's copper 2. And you always end up having the wrong one. Anytime you need copper 1 oxide, someone says copper oxide. Anytime they mean copper 1 oxide, you end up thinking it's copper 2 oxide. Anytime they say copper 2 oxide, you end up thinking it's copper 1 oxide. There's just like copper 1 and copper 2 versions of everything. And everyone always just says copper and never clarifies. It's a nightmare. And then you're doing copper 2, and you're doing your copper 1 stuff, and then it just spontaneously turns into copper 2. And so you have to add more copper to fix the copper. So you put pure copper metal in your reaction to reduce it back to copper 1. But then that doesn't work under certain conditions. It's just a nightmare. The copper 1 to copper 2 thing is a nightmare. But obviously, having electronics and wires and things, and copper is very, very useful. So I think this all balances out, and it goes into A tier. Anyone who says copper belongs in S tier has not experienced the true pain. Intel also did something similar with the DEC Alpha Arch. Oh yeah, I mean there's a long history of patent stupidity happening. All right, that's copper, though. I also have some vague recollection of something called Naturkopfer. What is that? What am I remembering? It's like an explosive thing? No, does this not exist? Oh, well. I have some vague memory of this. If you know what this is in chat, it just popped into my head. All right. Moving on to our friend Zinc. I realize I'm just doing all the main group in order, but whatever, it's fine. I know I said I was going to do in groups, but it's all right. We're going to speed through these ones a little bit. I will tell you, there's not too much interesting about a lot of these, but there's some fun ones. Zinc is important for life, but other than that, it's kind of not that interesting. It's very commonly used for like batteries and stuff too, because you can use it, I believe, as an anode. It's a reducing agent. Oh, I forgot one thing about nickel. Nickel is also used sometimes for like hydrogenation reactions or something. There's something called rainy nickel, which is the way you make it is kind of weird. You basically make like an aluminum and nickel alloy, but like in solution of water, and then when you extract out, you get tiny particles of nickel, and you make an aluminum nickel alloy, and then you get rid of the nickel, or you get rid of the aluminum, and so you're just left with a bunch of teeny tiny particles of nickel, which makes for really good catalysts for doing like hydrogenations and stuff. So that's when if you have a hydrogenation is here's a double bond what I want to do is, instead of a double bond, just stick 2 hydrogens on there. So here's your hydrogen, here's your hydrogen. Right, and you can use rainy nickel to do that. But yeah, rainy nickel is a fun little thing. It's also cool because it's pyrophoric. If you don't know what that means, that basically means, so if you think about it, like most substances have some kind of auto-ignition temperature, which is just, I'm throwing so many words out there. But you have some kind of temperature where when you're above that temperature, it will ignite. Pyrophoric means that the auto-ignition temperature is below room temperature. So at room temperature, just sitting there, it can just catch fire. It's very, very cool and fun. And rainy nickel is pyrophoric. So that's the last thing I wanted to mention about nickel. I knew I was going to remember it. All right, zinc though. I mean, zinc is cool for life. We're alive. We need zinc to be alive. But I don't know. It doesn't do that much interesting stuff. There is a fun story about zinc, which I mentioned were organometallic compounds. There's one called diethyl zinc, and there's a very fun story about it. DES, yes, it's called DES. Does it not know? Oh no, Wikipedia, you're failing me. The one thing I keep opening over and over again in the stream to show pictures and whatnot is failing me. Diethyl zinc. There we go. There's our friend diethyl zinc, because I can't draw for my life, but you get the idea. I probably could draw this one actually. See, it's diethyl zinc. There we go. Yay. But anyway, diethyl zinc is a useful chemical reagent, but there was a proposal to use it on books to preserve books from getting degrading over time. And it worked to keep the books from degrading over time, but had the minor problem that diethyl zinc itself is pyrophoric. So it could just, putting something that can just spontaneously catch fire at room temperature inside your precious books is not a good idea. So that was a funny, questionable idea, and my computer is dying again. But yeah, that's a fun little zinc story. Hopefully my computer will stop letting me go. Don't give me up. Okay. All right. Cupric versus cuprous oxide. Yeah, exactly. Copper 1 versus copper 2. It's a nightmare. It's a nightmare. Yeah, but yeah, zinc is all right. Zinc is a. I'm done. Zinc is all right. I think I'll put it in C. Zirconium. Zirconium is a very hard metal. I mean, I mentioned zircanocenes already for catalysis, which is kind of cool. There's not that much crazy stuff you can do with zirconium. A lot of times it's just used titanium didn't work, so we can try zirconium, and if that doesn't work either, we can try hafnium, I guess. Right, and especially in a material science context, this is kind of these groups form kind of your grab bag. Zirconium's not that interesting, though. I mean, sorry, zirconium, but where's zirconium? There we go. Should zinc go higher? I feel like some of these I'm underrepresenting. Should I make a C- tier? What do you think, chat? Should I make a C- tier? Should I make a poll to make a C- tier? Do I make a C- tier? Because I really feel like there should be a C- tier. Yes. Nope. Nope. I really am not sure. But I'll leave it there for now. Then I can split them up in a second. Niobium. Niobium is it's used to make alloys of metals. It's used for metal stuff. That's about the only interesting thing I know about it. Oh, also zirconium is used to make fake diamonds, I think. But yeah, niobium is used to make metal alloys and stuff. It's whatever. Niobium I'm doing it. I mean, let's see what chat says. Oh, it's tied. It's tied. Should we make a C- tier? Well, then if it's tied, then I am going to break the tie and say that yes, because I want a C- tier, and I just want it, okay? Let me hit my C- tier. We'll do, add row, wait, this is C minus, add row below, and then light blue. No, I don't want you to be light blue. Frick. There we go, this is C minus. And this is just C. Okay, wait, fuck. This is just C, there we go. So C- tier, let's, maybe I should have done it C+, whatever. Sodium is definitely pretty cool. Cesium is meh. Calcium is, I don't know, meh. Strontium, I mean, the flame color is pretty pretty. I'll give it that. Lanthanum is cool. Cerium is not. Praseodymium is cool. Europium is cool. Holmium is meh. Gadolinium, I mean, MRIs are cool, but like, I don't know. Well, you can go over there. Thank you, computer, for dying. Titanium, C-, manganese, the zinc, zirconium. Yeah, we'll do that. We'll do that. Actually, yeah, that's good. That's good. And then we can put niobium in. I mean, the thing is, niobium just doesn't do anything. Like, there's just nothing. Oh, zirconium should go here. Let's do that. Molybdenum. Molybdenum sure seems like just any other boring, the lame transition metal in the middle of the pack. But there's one very cool thing that it can do. Quadruple bonds. Ha. Wait, it's chromium. No, not quadruple. There's like quintuple bonds. Yeah. There we go. Molybdenum and tungsten. Tungsten can do this too, to be fair. Can form sextuple bonds, which is just ridiculous. Like the fact that we even have quadruple bonds, which can form between chromium. Honestly, that's pretty cool. Where did I put chromium? Okay, chromium's getting promoted. Get promoted, chromium. There you go. Quintuple bonds, I believe we also can do with chromium. Yeah. And so chromium and molybdenum are both used you can make quintuple bonds with both of them. But yeah, and then you need either tungsten or molybdenum. You can make sextuple bonds, which is just hilarious. It's just so funny that that's a thing you can do. I mean, like, again, like, what is they didn't even bother drawing that because it's like molybdenum, 1, 2, 3, 4, 5, 6. It's like, what is this? This is not real chemistry. This is just like a ladder that I can climb up. This is a treehouse. I'm so good at drawing. Yeah, this is not right. And then these are cows saying "moo" by your tree, right? Because your tree is in the middle of the field, and then here's the cows. I'm so good at drawing. I'm dying. What am I doing? Okay. Anyway, molybdenum's cool because it could do that, but that's really all there is to it. C- tier. Actually, C minus. Actually, C minus. Yeah, we'll do C. C minus. Technetium. This is the other. I mentioned promethium is the other one. This is the promethium is number 2. This is number 1 of the elements that, even though they aren't past bismuth, they're still radioactive. It's used for some like nuclear medicine stuff. It's all right. One of the fun things actually is that if you ever notice, you'll see the isotope that they usually use for like nuclear medicine stuff is not technetium-99. It's technetium-99m. Oh, again, some of you might remember this from the radiation shielding video, but this indicates a metastable state. So you can have something where, like, let's say I have the example, I'll use the same example from the video, which is if you have americium-241 inside your smoke detector, then what is happening is it's decaying to neptunium-237. So here's, why am I rating this so crappily? I'm switching to Excalidraw. It's Excalidraw time. Hopefully I don't have anything important here. Oh yeah, don't worry about this. You can't see what this is. It's fine. This is maybe for a secret project, but you can't understand what anything is because you don't have the power of context. All right. Let's see if I can draw a little bit better here, if I can remember what I was drawing. Yeah, all right. So we'll do this. This is like energy. Oh, this is so much better already. Why did I do this from the beginning? So this is energy, and what we have here, this is americium-241. And what happens is americium-241 decays into neptunium-237. But it doesn't do it directly. So here's our neptunium-237. Oh, freaking hell. I love getting my battery exposed on stream. All right, here's neptunium-237, but it doesn't happen directly. What happens is it first decays into this sort of metastable isomer. So this right here is still neptunium-237, but it's not the normal stable version of it. I like to think of it like it's the right nucleus. It's the right things making up the nucleus, but they're just sort of in the wrong place. So this is neptunium-237m. And what happens, is you have this transition first, and then very, very quickly it goes here. So the way we know that this is a thing is because this transition releases alpha particle, this one releases a gamma, a gamma radiation, and we can detect both of these. What's cool about technetium, and the reason TC99M is there, is that it's kind of like this. Here's our TC99M. This is TC99. The catch is that technetium is a very, very long-lived metastable state, right? So it's not like the whole smoke detector neptunium case, where it decays like basically immediately. This decay happens basically immediately. This happens over a long enough period. And again, what's nice about this is when this decay happens, you're releasing gamma radiation. A lot of isotopes, right, like that will release gamma radiation might also release other byproducts. And those other kinds of radiation, gamma radiation is the least harmful like inside your body. Right? Gamma radiation is about as harmful inside your body as it is outside your body. It's just based on distance. Whereas something like alpha radiation is like 20 times more dangerous inside your body. It's very, very dangerous to have alpha particles inside your body. So you want to basically be as close as you can to just having a pure gamma emitter. And so in medicine, we often use technetium-99. So that's pretty cool. It's cool that it's this weird anomaly. Technetium gets, let's get B tier. I think it gets B tier. All right. Ruthenium, I don't know that much about ruthenium. I don't know what to say, man. It's a D tier. Yeah, it's like dysprosium. Like there's like literally nothing I can think of. Rhodium. Rhodium is all right. It's there's this. It makes cool colors. People make cool colors with sometimes. It's really, really expensive. Where's the other cool colors? Yeah. So if you have way too much money, you can make cool complexes of different colors with it, which is fun. It's also used sometimes. I mentioned when you're building like an X-ray tube, right? What you basically have is just like a source of electrons. Here's your like whatever. The point is you're shooting electrons out of something, and when those electrons hit your target, then they produce X-rays. Yay! X-rays, yay! Radiation. What happens is there's different materials you can make this out of, and one of the ones that you can make it out of is rhodium. I've seen that sometimes. So the rhodium has some usage. It's not the craziest thing ever, but it goes in C- tier. Palladium. Palladium is very, very important, I guess you could say. I mentioned hydrogenation reactions before. When you have, here's your compound with a double bond. Again, this is just some random molecule I made up. Let's just, whatever, sure. Right? And you want to replace, instead of having a double bond here, you want to have just hydrogens. So here's your little hydrogens. Palladium on carbon is a very common way to do this. So it's usually written PD/C, but it's basically just a mixture of graphite and palladium. The other thing you can do with palladium, actually involving hydrogen, oddly enough. So the way this works, I should note, is that you put hydrogen gas into this reaction. But one of the crazy things that palladium can do is if you have the palladium metal, a matrix of a matrix of palladium metal can absorb hydrogen gas, like a huge amount of hydrogen gas, into the matrix of metal itself. So if I look up, I think sometimes people even refer to it as a single compound, as though it's like palladium hydride. Palladium. There we go. Yeah, so it's a palladium metal with hydrogen infused into its crystal lattice, and it acts like an alloy. So other metals can actually do this to some extent. And so what happens is as you add, you want to basically keep those metals away from storing huge amounts of hydrogen, because hydrogen will diffuse into them and make them more brittle, because it's basically infiltrating. It's infiltrating the crystal structure and just disrupting it a teeny bit. But palladium takes this to a whole other level. You can fit. It's like the meme. You can slap the back of a car. You can fit so much hydrogen in that palladium. So that's another really fun thing that you can do. And since people are trying to use hydrogen as like a greener fuel, there's been quite a bit of interest in ways of storing it. So palladium's fun. It's really quite useful. It's also super expensive, but it's all right. It's deserving of C tier. It's going in C tier. All right, silver. Silver's great. I mean, obviously it's expensive and shit, but it's not it's not gold, right? Silver goes below gold for a reason. Silver is very, very useful for photochemistry. So, for example, silver iodide is very, very weakly bonded, and you can basically break that bond with light, and then that can leave deposit metallic silver on the page, and then you can do all kinds of stuff with that. Silver is very, very important for photography and whatnot. There's also, there's also, what is it called? I think it's RbAgI5 or something. Rubidium silver iodide, which is, or silver iodide itself can do this too. Certain silver compounds can do this crazy thing where it acts like a conductor of electricity, right? So a normal conductor of electricity is because you have your thing and you have some electrons, and the electrons are mobile, right? They can move around. So here's your electrons moving. I should really use the number keys for this. What you can do is a lot of silver compounds can form what's called certain silver compounds, I shouldn't say a lot, can form what's called an ionic conductor, where it basically does a similar kind of thing, but instead you have silver ions going the other way. So you're taking this huge, instead of moving little electrons around like normal, you have mobility of these huge ions going around. It's really cool. So rubidium silver iodide is one of them that's actually very good at it. But I believe other forms of silver iodide can do it, just not as well. Yeah, rubidium silver iodide, RbAg4i5. I was close. Yeah, it's really crazy, especially because silver is not we're not talking about hydrogen or something, right? Silver is element 47. That's a big, big atom to be just moving, having it slide around. It's crazy. So silver is really cool. I think silver gets A tier. Do I think it gets A tier? B tier? We'll put it in B tier for now. All right, cadmium. Cadmium is very, very useful. It's unbelievably useful. And it's also toxic as shit dicks. So the solar cells that we make are cadmium tellurium. The thermal cameras are, I believe, mercury cadmium tellurium. If you're noticing a pattern here, tellurium is also a little bit quite toxic. But cadmium is kind of, I mentioned nickel cadmium batteries. The cadmium, if you've ever done any electronics, you'll recognize these photoresistors. These, a lot of times, the actual element that's doing the photoresisting, right, where you shine light on it, its resistance changes. A lot of times that's cadmium, either cadmium sulfide or cadmium selenide. It's some kind of, chalcogenide. I said in the very beginning of this that no one ever says chalcogenide except to say chalcogenide salt. That's what I'm doing now. It's oftentimes cadmium. It's a chalcogenide salt of cadmium. So it's cadmium and then one of these elements, usually CDT is used to make solar cells. CDS or CDSE, usually, I forget which one is more common, is used to make photoresistors. And so that's pretty, again, cadmium is very useful, but its toxicity is also horrible, and its environmental toxicity is also horrible. And it's just bad, but it's really useful and cool, so I think it all balances out, and it gets put in a C tier. C minus tier. All right. Actually, solar panels are pretty good. C tier. We like solar panels. Okay. We're getting there. We're getting through the transition metals. We have hafnium. You really can't do that much with hafnium, man. It's really strong. You can make strong stuff with it. It's for D tier. Freaking D tier. Tantalum is an element that there has been effectively, obviously it's hard to define these things, but something analogous to a civil war over, because it's such a rare element, yet it's incredibly important for modern electronics. But it's a really cool element. It's used to make capacitors, which, if you don't know, a capacitor is literally just like two plates of metal next to each other, and the idea is that you can store charges on either plate of metal. And tantalum is used to make a lot of capacitors, and so it's very important for modern electronics. It's also one of the elements. A lot of elements are in this case, unfortunately, but tantalum is one of the elements that's also not very rare, and it's mined in miserable conditions, and that part of it is bad. But yeah, it's all right. Tantalum is I think also used the way rhodium is sometimes for X-ray stuff. Another thing about these is I should mention the concept of refractory metals, which is basically the idea of metals that you can basically throw anything at them and they're fine. So they don't really react much with acid and stuff. So gold is a classic example of a refractory metal. Tantalum, I think, is generally considered a refractory metal too. So if you're trying to, a very common use of tantalum in like a lab is if you have, you have something that you want to go put in a furnace, and some crazy arc furnace is going to get to like 2,000, 3,000 degrees Celsius. Oftentimes the boat, it's often called a boat, but like whatever the thing you put your sample in is going to be made of tantalum, because it will be able to hold, it'll be able to stay up, it'll hold up to that heat. So tantalum is quite useful, although the whole Civil War thing isn't great, but I think it goes in a C- tier, sure. Tungsten's really cool. So I mentioned the quadruple bond thing that molybdenum can do, tungsten can do too. Oh, hey, look at that! Remember how groups do have similar behaviors? If you want to make a ton of, anything more than a triple bond, your options are chromium, molybdenum, and tungsten. That's so cool. Yeah, I love it when my point gets inadvertently proven. But yeah, tungsten is great for radiation shielding. It doesn't have the highest melting point of any metal, but it has almost the highest melting point. We can see actually here. The melting point of tungsten is about 3,400 degrees, I believe. Whoa. Whoa. I thought osmium's was higher. Oh well, maybe it does have the highest melting point. I don't know. Don't ask me. Okay, I don't really know what to do. Now, I didn't know you could do this with the table. That's kind of cool though. That's fun. Anyway, I guess it's up for debate maybe, or I'm just dumb. But I thought tungsten didn't actually have the highest melting point. But regardless, tungsten is an extremely high melting point. It's used for incandescent filaments. Filaments and incandescent lights, which incandescent lights suck, but it's still cool that it can survive up to. It can survive those conditions. And tungsten's overall a pretty cool element. We'll put it in. Do I put it in B tier? Is it that good? I'll put it in C tier for now, but if I come up with something else, I can put it in B tier. Rhenium, it's expensive. I don't know much else about it. Oh yeah. Wait. I do know something about it. There's potassium. I can't talk. Potassium, nonapyrenate? No, it's, what is it? Nonahydrate? It's like KREH9. I think you can do a sodium too. NaREH9. It's a compound. There we go. Potassium, or let's just do the sodium salt. Sodium nonahydrarenate. No, tell me what it is. Oh my gosh. Hydrorenate. I'm dying. Rhenium. Fine, freaking rhenium compounds. I want to show you the cool picture of it. I have a picture of it on my wall in my dorm room because I think it's wild that it exists. Yeah, this is what we want. Although, will it show the sodium one? No, it's not going to show this. Whatever. This is the lattice of potassium hydrorenate. That's how you spell it. It's hydrorenate, because this is actually a shitty diagram where it's hard to see what's pointed to what. But basically, I mentioned forming the complexes and compounds. It turns out rhenium can bond to 9 different things. In this case, it's bonding to 9 different hydride. There we go. This is better showing it. It's a single rhenium atom bonded to 9 different hydride ligands. Right. So this is a ridiculous coordination complex. It's like 9. You have 9. Seriously, 9. You can fit 9 on there. So that's pretty cool. That's the one cool thing about rhenium. I don't know. It's C- tier. One cool thing isn't enough, even if I'd like it. Osmium is the very expensive, and it's used for some stuff. Osmium tetroxide is sometimes used as a reagent, although it's very, very dangerous and awful to deal with. Yeah, there we go. Highly toxic osmium tetroxide. It's used for some stuff. I don't know. It's not that much. D tier. Iridium. Iridium is used for making cool coordination complexes. There's some medical applications I know of iridium coordination complexes. It's another refractory metal. It's not that. There's not that much you can do with it that I know of, at least. other than making some cool coordination complexes. Maybe, do I put it? No, it doesn't deserve C minus. Platinum, it's expensive. That's about all I know. T tier. Even if there's like one cool thing about platinum, it's I can't talk. It's too expensive. Gold does some cool stuff. There's the fun story about how during World War II, who was it? I can't remember the name, but it was someone who like won the Nobel Prize, and I think it was chemistry. Let me actually catch up on chat. Cubic zirconia is cooler than diamonds. Oh, I'm so behind on chat. Sorry, I totally forgot. Cubic zirconia is cool. Yeah, so cubic zirconia is often used as a substitute for diamonds. Molybdenum is cool in metallurgy too. Nice. Also used for making. Right. So if you want to make, you synthesize the technetium isotope. You start with molybdenum and then react with it. Explosions of fire try to do the rhodium rainbow. Yeah, I know. Is that like a hydrogen clathrate? I never know how to say the word clathrate or whatever that is. However you say it. Iridium is cool because you can chew it. I think you're thinking of indium. Iridium is a very, very hard refractory metal. I think indium is the one you can chew. And I don't know I forget the exact definition of clathrate, but it's a similar idea, right? You're impregnating it into like an existing lattice. So it's kind of like that, yeah. And tungsten is definitely the highest melting point. You might think of how, hey, you're right, you got me. Osmium and iridium are contested to have the highest densities. Yes, you're totally right. That's what I was thinking of. I was reading about that too, because like density is such an important thing for radiation shielding. Touchscreens are made with iridium, are they? I thought that was indium too. I kind of thought that was indium too, but maybe I'm wrong. But yeah, I really don't think you can chew iridium. I think you're thinking of indium. But yeah, platinum is meh. Where did platinum go? Did I already? Oh, I already put it there. Gold. Oh right, I already did platinum. We're on to gold. Gold is cool. It's very resistant to basically anything. There's I was just saying the story about where so basically they got the gold for the Nobel Prize and like they took the gold medal and dissolved it in aqua regia, which is I think it's just a mixture of nitric and sulfuric acid. Hopefully I'm remembering that right. Anyway, it's the mixture of acids to basically dissolve, which is one of the only things that can dissolve gold. And so they literally dissolved away like the prize in order to hide it, so that it just looked like any other jar of chemicals or whatever. And then they could reform it at the end, which is a fun little story. But I think it gets C minus tier. I'm never going to do any gold chemistry in my life. It's too expensive. It's fairly obvious. Mercury. Mercury is also really useful. So mercury is in kind of the cadmium lead camp where it's like really, really useful, but also toxic as frickin' frick. But it also has the coolness factor, right? Like lead is useful. Cadmium is useful, but mercury is useful and cool because it's a liquid metal at room. It's a liquid metal at room temperature, and that also is I should note that it being a liquid is also useful for stuff too, because you can like pump it around and shit. Yeah, man, I think mercury gets higher marks than whatever I put cadmium as. So B tier, does it really? It goes into. It's so cool though. All right, we're putting it in. Does it deserve A tier? Oh, this is so hard to do because it's so freaking toxic. It goes in B tier. I'm taking into account toxicity. All right. Then we have rutherfordium, bemonium, seaborgium, bohrium, hassium, and these are the transactinides, and I don't really care about them. Again, there isn't really too much to say about them. They're going in D tier, if I can find them. 103, 104, 105, 106, 107, 108. There's not much to say about them. I'm sorry. All right. Now, it's time to move on to our little group over here. Or do we want to do the actinides? Let's do the actinides at the end. That makes more logical sense, I think, because bigger numbers. Boron. Boron is awesome. Boron is really cool. I mean, again, maybe I'm a little bit biased because I used boron to make freaking antimatter, but like, boron's great. It can form these super dangerous. Okay. I'll just draw it. I'll stop gripping, just showing pictures from Wikipedia. I'll try to actually draw some things. Boron can make. Hopefully, now I'm worried I'm drawing it wrong. Oh no! But boron makes this compound. I'll just draw it like this. Where you've got your boron, and it looks like this. What? I think it's also like this. But yeah, like what is this? Why is hydrogen bonded to two things? What the frick is this? This molecule is diborane, and it's pyrophoric. It's very toxic. Yeah, there we go. See, I had it right. I know chemistry. And it looks like it totally shouldn't exist at all. What the frickin' frick? But what's actually happening here is these are not normal bonds. These bonds are kind of a lie. Instead, what we have is... Oh, wait, can I erase things? Do I have an eraser? I do have an eraser. Ha-ha. Instead, what we really have is these kind of 3-center, 2-electron bonds, I think it is. But you have this super weird non-standard bonding structure. And it turns out you can even get crazier boranes. Like decaborane is a good one. Like what? What is this? Whomstidiv? Yeah, there you go. You can see the non-standard bond, non-classical bonding over there too. It is crazy. It's crazy. Boron is useful for like the boric acid and lots of stuff. Hi Zeno. Hi Miras. Hopefully I'm saying that. Sorry, iridium is the spark plug metal. Yeah, you were thinking of indium. Yes, iridium is used for spark plugs. You're completely right, I think. Hi Miras. Hopefully I'm saying your name right. I don't know exactly how to. Apologies if I am not. All right, but yeah, boron can do like non-standard bonding. These boranes were actually like investigated as rocket fuel because they're so incredibly dangerous and reactive. But yeah, I talked about boron. I use boric acid for stuff. There's boric oxide. Also, boron nitride is like there's a form of it called called cubic boron nitride, I believe it is. Or it's like the diamond-like boron nitride. But anyway, it's incredibly hard material. So I mentioned tantalum, sometimes like crucibles or whatever that you're using for like super high temperatures in a lab. There'll often be the crucible will be made of something like tantalum. Boron nitride is another option. Yeah, where is it? It's like the cubic form. Yeah, cubic boron nitride is a crystal structure. Analogous to that of diamond, and it's a very very strong. It's a very very strong material, which is really cool. I believe boron carbide is also quite strong. So there's lots of like crazy super hard materials you can make with it. Boron's just freaking awesome. I love some boron. I think A tier. Aluminium, depending on which side of the Atlantic you're on. It's cool. I don't think it's all it's cracked up to be. I mean, thermite is pretty fun, right? Thermite's pretty fun. But, I don't know. Aluminum's just handy and fun, and there's the chlorides are a useful reagent, and obviously people, aluminum foil is easily accessible and useful and stuff. It's all right. Yeah, I think aluminum is maybe a little bit overrated. So we're putting it in C- tier. All right, gallium. Gallium is dope because gallium, not a liquid. I don't believe it's a liquid at room temperature. It's a liquid just above room temperature, right? And so it can form. If you like warm it up with your hand, it turns into a liquid. If you warm it up just a little bit, it turns into a liquid. It's really cool. Yeah, it's freaking awesome. I actually should make sure. Melting point of 29 Celsius. Yeah, so room temperature is 25 for any of you in freedom units. But like, come on. Oh wait, that's not what I meant to do. Yeah. It's awesome. The fact that it's a liquid is awesome. It's also used a ton in semiconductors and stuff. So gallium nitride, you might have even heard about. Like, it's even like even like on the consumer side of things, you might have heard about gallium nitride. But yeah, people are doing all kinds of crazy stuff with it. It's very useful for semiconductors. As a liquid just above room temperature, which is awesome. Gallium is just great. It's just great. It has quite a nice spark color too. Where's gallium? Where's our friend gallium? Gallium is S tier in my opinion. It's high praise, but I think it deserves it. Does it deserve it? Yeah, I think it deserves it. Gallium nitride kind of seals the deal. Indium is used in touchscreens and stuff as. I want to make sure I'm getting the person right. Yes, Stumpy Bumpo said. This lithium alumina hydride comes as a point in aluminum's favor. That's a good point. That's a good point, actually. I hadn't. I think that would count mostly as lithium's. As a point for lithium, which lithium I already put up pretty highly. Although I am tempted to kind of move it up a little bit. Here's what I'll do. I'll move lithium up one to compensate for that. It's true that aluminum that is a cool thing, but like I think it still belongs here. I'll give those points to lithium. Anyway, indium, I believe it has like the distinction of like the only metal you can like put in your mouth or something, or like maybe the only metal you can chew. But yeah, it's a soft metal, and it's mostly non-toxic. It's used in some semiconductor stuff. It's used in Yinmin blue. Yinmin blue. There we go. The pigment that I talked about earlier. It's pretty cool. There isn't that much to say about it, but it is quite fun. So I think it's getting C tier. I think that's fair. Thallium. Oh, thallium. Thallium is extremely toxic, and it was used. I think in like historical context, it was even used as something of a poison. But it's just really, really toxic. It's one of the only cases where, like, for example, chromium. In the case of something like chromium, right? The metal is totally fine, and you eat with it every day if you use stainless steel forks. But as soon as you start making compounds with it, then you're in the really toxic territory. Thallium, the metal itself, is actually toxic. It's something like beryllium, but it's a very, very different mechanism. Thallium is very, very toxic. It does have one redeeming quality, though. I mentioned that I talked about scintillators before. Our good friend, how do I do this? Whatever. Our good friend scintillators, where which are used for detecting high energy gamma radiation. One of the most common types of scintillators, in fact, the one that I use for doing the antimatter detection, is sodium iodide. And cesium iodide is another one. I actually have a cesium iodide scintillator that I got for cheap on eBay, but I haven't done anything with it. It's just like, it was such a good deal that I was like, I'm probably going to need it at some point. It's worth the risk of me. I'm going to use it eventually. Eventually, I'm going to build my own scintillation detector using my cesium iodide that I bought on eBay. But the one that I used for the antimatter project was sodium iodide. And these by themselves work as scintillators, kind of, but they don't really emit the right wavelength. If we want them to emit in the visible spectrum, we got to dope them. And you generally dope them with thallium. So this is the one redeeming quality of you got a sprinkling bit of thallium for scintillators. And I love scintillators, but I think honestly that only really moves it up to like D tier. So where's thallium? There it is. It's toxic, man. It sucks. Then, did I already rank all those? Whatever. It's fine. I can put nihonium. Actually, we should do something special with this. So I mentioned these are the transactinides, and there isn't really that much to say about them. They just exist. They were for a very short amount of time. But if I can find nihonium, as a weeb, I think I'm legally obligated to put it in S tier. So we'll go ahead and do that. I think that's the correct thing to do. And then we can move on to carbon. Make sure I'm caught up with chat. I am. All right. Carbon, the favorite element of organic chemists, the backbone of organic molecules. It forms graphite and graphene too. And organometallics are pretty fun too. And then that only happens because it's carbon. That's like the whole point. And carbon is pretty cool. And even if you restrict yourself to like just carbon and hydrogen, you can still make cool compounds. It's crazy. There's a whole class of compounds that are called like polycyclic aromatic hydrocarbons. So I mentioned aromaticity is when you have like delocalization of electrons. So instead of like this is benzene kinda, but in reality it's all delocalized and it looks like that. But you can combine these rings together and make all kinds of different patterns, and these often have like cool fluorescence properties or something along those lines. It's very fun. So there's a ton of polycyclic aromatic hydrocarbons, and other than hydrogen, it's literally just like carbon. So hydrocarbons, there's like oil and lame stuff, but there's lots of cool stuff, and there's an endless variety of what we can do with carbon. So I think carbon, much to the happiness of the organic chemists, is going in C tier, C for carbon. All right. Now that everyone is leaving, oh, I should end the poll about C minus tier. Well, at least people agreed with me in the end. No. Yes, carbon is really cool. No, I'm being facetious. I'm being silly. Frick. There we go. Carbon is definitely S tier. Carbon is absolutely S tier. You can do so much cool stuff with carbon. You can make carbides. A lot of the cool, like, weird material science stuff even involves carbides. Boron carbide is super strong. Lots of electrides are carbides. It's great. Carbon is definitely going in S tier. All right. Silicon. Oh man, you can see this is the good section. We're saving the best for last. This is why we're not going in order of just I mean, there are many reasons we're not going in order of the numbers, but we're really saving the best for last here. Silicon is very, very important for electronics and stuff. There's some of the stuff you can do other stuff, like gallium arsenide, for example, is also a common semiconductor. But silicon's just so useful. It's just the basis of everything we do with semiconductor technology. It's really cool in its own right. Silicon dioxide is quartz, which is also really cool. My voice is dying. And it's just, we have silicon dioxide, which is quartz, but there's also silicon monoxide, and there's a kind of cool, the way the oxides in silicon work is quite cool. There's also, I mentioned pyrophoric substances where they just spontaneously ignite. The silicon analog of methane. So if you take methane, but you replace the silicon with hydrogen, you get silane. And silane is, as far as I know, it's basically the only pyrophoric substance that isn't toxic. So it isn't supremely toxic. So it's not that, much of a pain to make. So, silane's really cool. But silane isn't just fun because, you can make it in a test tube and then woohoo, you get to show a pyrophoric substance. It's also used to deposit like pure silicon onto chips. If you have pure silane gas, you can, have this set up a reaction where when this, deposits on your chip, you get pure silicon out of this. It's just really quite cool. So silane's pretty cool. Silicon in general is obviously super important and cool. I think silicon also goes in S tier. S for silicon. It's perfect. Where are you? There we go. Then after that, we have germanium. Germanium explosion. I'm going to reference explosions of fire again. He referred to germanium as your backup silicon, which is kind of true. Except silicon, most of the time silicon just works. Very rarely do you have to go default to germanium. But one of the really cool things about germanium is that it's transparent to infrared light. So you can make infrared lenses and stuff are made out of germanium. But the fact that it's just transparent to infrared light but totally opaque to visible light is really, really cool in my opinion. There's lots of fun material science stuff you could do with it too. It's pretty great. I really like germanium. I might play with it at some point. It's going in A tier, I think. I'm tempted to put an S tier, but I don't think that will. W take for real. I'm not sure what take was my W take, but I'll assume it refers to tungsten. I'm assuming you're saying my tungsten take. All right. So many good ones. Then we get to tin. Tin is fine. It has a very low melting point. It's easy to work with. I used it in the radiation shielding video in an alloy. It's all right. There's some organostannine compounds people use. Again, stannane just being like tin, because that's what the SN is. It's fine. I think it gets C tier, C minus tier. Yeah, C minus tier. We're doing C minus tier. I think putting it into the same one as aluminum is good. Then we get to lead. Lead is so useful. It's perfect for everything. You can make perovskites. You can do all kinds of amazing stuff. It's cheap. It's incredibly abundant. You can just it makes good radiation shielding. It's so good for everything except for the minor inconvenience that there is no safe level of lead. A lot of stuff, if you have it in there's a small amounts where it's really fine, and then there's a threshold at which it starts becoming dangerous. With lead, as far as we know, the threshold is 0. So, yeah, that's not great. But lead is still very useful, and as long as you're not dumb about it, it's just too useful for me to put it in anything other than, let's put it in the same tier as mercury. Well, no, the thing is mercury is cool, right? Lead is useful. I said this before. Lead is useful but toxic. Mercury is useful and cool but toxic. I think that's good. All right. Flerovium. Again, this is not a transactinide I can make a fun joke out of or something, so if I can even find it, you're going in D tier, just like the rest of them. Nitrogen. Nitrogen is crazy. Like, first of all, if you want to make anything energetic, or, we talk about like TNT is trinitrotoluene, right? So nitration is you put in thing, you get out thing, but either very flammable and in some cases maybe explosive. Like it's crazy. That nitrogen, there's just so many different things you can form out of nitrogen, right? You can form, I clicked the wrong thing, right? You can form like cyanide if you have, C triple bonded to an N. You can do nitro groups, which is what I talked about for nitration. If you want to make things go boom. There's, I think I drew that right. I don't remember the exact structure. Again, I'm not actually like much of a chemistry person yet, but you can just do so much stuff with nitrogen. You've got your NO2, you've got your NO, and nitric oxide is actually super cool unto itself, and it's used as part of your nervous system. And nitrogen is just great. It's just useful. Also nitrides. So, like I mentioned, gallium nitride, right? You can make compounds just with nitrogen, and it's pretty cool. Nitrogen is pretty cool. If I can find it, I think I will put it in, not F tier, no way. Let's put it in A tier. I think it goes in A tier. Does it come in B tier? I think it goes in A tier. We do, 70% or whatever of the air is nitrogen. And also liquid nitrogen. Liquid nitrogen is dope. Yeah. It's definitely A tier. Definitely A tier. I love that I just wrote the word no. I didn't even realize it. For anyone, this is nitric oxide, not the word no. All right. Phosphorus. Oh boy, phosphorus is just stupid. It's really useful. There's lots of stuff you can do with it. For example, phosphorus pentoxide is a very, very good dehydrating agent. So it's a very, very good desiccant. It will absorb water from its environment very well, and it'll turn into phosphoric acid. It's a lot of there's like phosphine and thiophosphane and stuff, and a lot of phosphorus compounds are pretty toxic and stupid. And there's everyone's favorite white phosphorus, which white phosphorus is pyrophoric. It's not that hard to make, but I will not be saying how to make it because it's incredibly toxic and bad, and it sucks, and everyone hates it, except people who like starting fires and making videos of starting fires at the cost of their getting sick. Really, nitrogen. Yeah, no, nitrogen's great. Nitrogen is great. All right. Where are we? Arsenic. Arsenic's somewhere in between. It's not as useful as like something like cadmium or lead, but it does still show up. It's in a lot of things. It's for like the semiconductor stuff again, where it's not like like thermal cameras are like often like made with mercury and cadmium. I'm pretty sure it's mercury, cadmium, tellurium. That doesn't mean that it's dangerous to use a thermal camera, but it means that the factories where they make the thermal cameras are full of very dangerous compounds. Arsenic, I don't know, it sucks, man. Arsenic sucks. I'll put it in D tier, I think, just because gallium arsenide as a semiconductor is quite cool, and it does have some uses. It's useful. But antimony also has some uses. I believe it was used for making like rewritable CDs, I want to say. I'm not going to bother checking that. It's fine. I'll put it in the same category as arsenic. They're basically more or less the same thing. They're just toxic, but sometimes have uses. Bismuth. Now we get to bismuth. Bismuth is dope. I love bismuth. Bismuth is so awesome. It makes great. Bismuth is like lead, but it has a lot of the same properties as lead, being right next to it. But is like the radiation shielding is a good example. But it's non-toxic. It makes these beautiful oxide layers that are all rainbowy, and it's so great. It's so great, and it's awesome. And in bismuth we trust. We love bismuth. S tier. All right, let me jump with that. Phosphoric acid is yummy. Isn't it actually used as a food? It's totally used in food, I think. Because it's used like Coke, right? Isn't phosphoric acid the thing that's like make Coke acidic? Or at least part of what makes it acidic? I think it is. I was reading about this earlier. Whatever. I'm actually pretty sure of that now. All right. Bismuth is dope. Oxygen. I mean, we do kind of need it to breathe, and fire is pretty cool, and liquid oxygen is also really cool. It's not S tier, but I think A tier is pretty good. A tier is pretty good. There is the problem of like oxidation is often sometimes you don't want, but sometimes it's something you do want, and I think A tier is right. It is rather important. Liquid oxygen is cool, and lots of stuff depend on it. Sulfur. I mean, I think we all know where this one goes. Partly because sulfur, or is it allotropes of sulfur? Partly because sulfur forms like 40 bajillion different like structures and stuff, and you can get different rings of it, and it's really cool. At present, about 30 well-characterized sulfur allotropes are known, with S8 being the most common one. So it's an 8-membered ring, and again, it's not planar. It's a different conformation, but yeah, it's crazy. But yeah, I think we all know what tier sulfur goes into. We're just gonna pretend that it doesn't smell horrible. All right. Selenium. Selenium is sometimes useful for very niche stuff. Otherwise, it's just a toxic and kind of a pain in the ass, and it's lame. Selenium is I think solid D tier. Honestly, I think selenium is just totally D tier. I would be putting it in D tier right now, but my computer keeps dying. There we go. Selenium, D tier. All right, we're getting there. We're in like the home stretch now. I can feel it. Tellurium again. Tellurium. I'm having a stroke. Tellurium is useful a lot in semiconductor stuff. I mentioned cadmium tellurium being used to make solar panels. It's quite a useful thing to have. The problem with tellurium is it is a little bit toxic, and it also does this thing where as soon as a little bit of tellurium gets in your body, your breath just like permanently smells fucked. It's super weird. It's cursed, and I don't get it at all. And please find something better to build solar panels out of. Please, material scientists, you can do it. I believe in you. We're moving on. Polonium. It's polonium time. Polonium is radioactive, so we've made it past. I mean, technically, again, bismuth is technically radioactive, but it's just the half-life is so long. It's you're almost never going to actually observe that happening. Polonium is radioactive. One of the most common isotopes, at least that's used, is polonium-210. So that is used. It's used as essentially it's a pure alpha emitter. So again, a lot of, like I mentioned, one of the problems with technetium is it's kind of hard to find an isotope that emits just one thing, right? So if you want it, the whole TC99M thing is used because you want to emit you want to get as close as possible to emitting just gamma rays. Polonium, PO210, is almost a perfect alpha emitter. And what that means is the alpha radiation can't penetrate through basically anything. Like people always say it's stopped by a sheet of paper. Like it's attenuated by a sheet of paper. It can pass through a sheet of paper. It's just hard. It's you're going to lose a lot of alpha particles on the way, or they're going to slow down a lot to be a little more precise. But it was used as a poison because the thing is it's a very, very difficult to detect poison. You can put a tiny amount of PO210 in there that'll be enough for the radioactivity to kill someone, because alpha particles are very, very toxic inside the body. But those alpha particles won't even be able to make it to any kind of detector that you have. So to a radiation detector, it'll look totally normal. Then they get poisoned and die and whatever. So there's a whole story about that. Then we have livermorium. I think we all know where this is going to go by now. Oh wait, I forgot to rank polonium. It's fine. I mean, the fact that it's a pure alpha emitter is kind of useful, but I think honest take here is D tier. All right, fluorine. If any of you have been up to date with the tubes of the U-tubes. Phosphoric acid is def in Coke, also used in old-timey sodas. Yeah. I remember that as soon as you said food, I was like, wait a minute. Oh yeah, it's the Coke thing. And also, I think even many different classes of sodas are, you use it. Arsenic is good because arsine has a funny name. That's fair. That's just fair. You have a point. All right, let me go back to this. I'm actually fluorine. So if you haven't kept up with the YouTube science, lab coats like with a Z recently made fluorine in his garage, which is a terrible idea. And he basically, at this point, he basically turned his garage into an actual lab and then made fluorine in a lab. But yeah, fluorine by itself is an incredibly powerful oxidizer, and it will destroy basically anything. Hydrofluoric acid, which is just HF, is used a ton in the semiconductor industry because it's used to etch silicon wafers. Except it can also etch glass. It can dissolve glass. That's how. The dissolving glass is both a sign of how the crazy powerful of an acid it is, but also an absolute, practically is an absolute pain in the ass because you can't use any glassware with it. Yeah, sure, there are other things that can etch glass, like concentrated hot sodium hydroxide can etch glass a little bit, but it's not like fluorine does it. And yeah, it's nuts. So oftentimes you're working with PTFE or Teflon, or sometimes PFA. Because that's it's all about time, right? If you're trying to store some fluorine for a very long time, which you generally just don't do, you would need to use something like Teflon, I think. But you can use fluorinated polymers like PFA if you're not doing it for forever, right? You're just doing it. It's just there for a little bit. It'll degrade a little bit, but it'll maybe passivate, but it's all right. Yeah, fluorine is just insane. Fluorine is terrifying, but in an insane way. And I think S tier, honestly, it's just wild. Yes, it's toxic and dangerous. It's freaking dangerous as heck. But it's just so crazy what it can do. It's so crazy what it can do. Actually, certain, I think platinum hexafluoride. I can't remember whether it's platinum hexafluoride or fluorinated peroxide. I think it's platinum hexafluoride. At least can do it. Is so strong of an oxidizer that it can literally oxidize oxygen, giving us something called dioxygenol. Yeah. What? You oxidized oxygen. What the frick? Chemistry has gone too far. Yeah, it's not. So it's used to react noble gases. We'll get to them in a little bit. And yeah, it's nuts. It's nuts. I think the order I'm going to do is after this, then we'll do the actinides, then we'll do the noble gases. I think that's fair. I think that's fair. It's a little bit out of order or whatever. Anyway, fluorine is totally crazy. Chlorine is, so the way this works is these are the halogens, and the ones up higher up are the more reactive ones, essentially. It's kind of the opposite of the alkali metals. But fluorine is the most reactive. Chlorine is still reactive, but pretty tame. Bromine is not that reactive, and iodine is quite difficult to react with stuff. Again, in this sort of vague scale. Obviously, they're kind of different. Fluorine is crazy reactive. Chlorine. So one of the things is halogens are often used in organic chemistry as it's sort of like a placeholder. Right, so if you want to do something, first you put a halogen there, and then you can connect other stuff to it. I know we talked earlier about Grignard reagents, right? That's kind of an example where you're using a halogen as sort of you're not trying to put a halogen in the final product. You're using it as just sort of an intermediate, like marker type. It's just sort of a marker, hey, this gets attached here, and oftentimes bromine is the best choice for that because chlorine is simply too reactive. But sometimes you use chlorine too. It's used a lot of chlorinated chemicals totally screw up the ozone layer. A lot of brominated chemicals do too, but chlorinated chemicals are the more problematic ones generally. Yeah, it's just chlorine is kind of lame. Yes, it's useful for making salts with, but the gas by itself is toxic. But it's not like fluorine where it's toxic in a cool way. It's just freaking toxic. And I don't know. I don't like chlorine that much. It's kind of crappy. Sorry, chlorine, but you get, this is maybe a hot take, but I'm putting chlorine in D tier. Yes, dioccidental hexafluoroplatinate. Yep. And how reactive is acetone? I don't think anyone really knows the answer to that, given acetone's short half-life. That's not true. I'm sure some people have. I'm sure we have a theoretical prediction of it, and we probably have some compounds. Like, we have made little compounds of these kinds of things. Like, people have made compounds like actinides, which is actually really cool. Like, it's this kind of actin. Well, we'll get to the actinides in a second. All right, where I'm getting ahead of myself. Bromine is, again, it's like chlorine. It's more useful for doing organic chemistry stuff. Bromine by itself is just a liquid, which looks really cool, and it looks like a evil boss or something. Like it just looks incredibly scary and cool. Bromine's great. We love bromine. Shout out bromine. I'll put it in A tier. Next we have iodine. Iodine. So iodine you can kind of use in a similar way. So one of the examples is, for example, you can make like iodomethane or iodoethane, which this would look something like this. And this is a very, very strong like ethylating agent. So you can react it with other stuff to add ethylene groups onto it. But it's also, these reagents are super toxic and an absolute pain. They're also gases. It's a nightmare. Everything's a nightmare. The iodine, like iodomethane and iodoethane stuff are just freaking scary. It's just freaking scary. It's kind of analogous to the chlorine versions. But iodine does a lot of really cool stuff. And one of the things you can do is why did I look up G-Show? I literally just randomly, like, you saw me type, like, J-I. Like, I don't know why that came to me. What am I doing? Excalidraw. All right. But anyways, so those sort of analogs kind of suck in iodine's case because it's just, the iodine carbon bond is just so weak, but there's lots of other fun stuff you can do with iodine, and there's this weird, cool thing that happens where if you have computer, I'm going to murder you if you don't let me use the mouse. Anyway, there's this cool thing where, there we go. And it happened again. What the fuck? Where if you have potassium iodide and iodine like in solution, it forms an equilibrium with the triiodide ion, which is kind of a fun thing that happens, and it makes like things that are like not supposed to be soluble, and it's a fun little trick. And it's cool. It does some cool stuff. I think I'd put it in like C tier, honestly. Why is my computer being weird? Astatine. Again, so normally I would treat it like one of the transactinides, right? Where it's just there and it's a thing, and I don't really whatever. It's kind of lame, but astatine is so fun to say. So it's getting artificially boosted into C- tier. For its the silly fact that it has a fun to say name alone. All right, and then tennessine. I already put. And we'll put tennessine. Since it's woods, we'll put it there. All right. We'll do the actin. How are we going to do this? Actinides and then the noble gases? Yeah, that's what I said. Actinides and then the noble gases. So actinide chemistry is really interesting because it's kind of like lanthanide chemistry, but also kind of not. And it's very, very hard to figure these things out because look at these elements, right? Uranium is one of them. It's very hard to do chemistry with uranium, and it's much, much harder to do chemistry with something like californium, where we produce a tiny amount of it in nuclear reactors, and that's it. So we'll start with actinium. I don't actually know much about actinium. I think it's kind of I don't know anything really interesting about it. The one thing about actinium actually is you might know that like vinegar is acetic acid, so it's something like CH3COOH, but like that but like that. So you have it's like CH whatever. The point is people will often abbreviate something like acetic acid as acetic, like an acetyl group followed by OH. So AC often stands in like organic chemistry for an acetyl group, and you can do other things, like praseodymium acetate with those pretty crystals. You can write like that. But it's confusing because AC is already an element. So like, come on, guys. Where is it though? There we go. We'll put it there. Thorium. Thorium has a lot of really interesting stuff to deal with nuclear. Thorium is, you can basically mutate the nucleus to turn it into nuclear fuel. And by itself, it's also radioactive and used in some like just general radiation products because it's one of the cheapest like radioactive elements. So thorium's all right. I don't know. It's fine. I think I'm honestly putting it in D tier. All right. Where are we at? Protactinium. Protactinium I don't know that much about. I know it's part of the like the decay chain of uranium and stuff. Or sorry, of neptunium, I think. There's these whole decay chains you can look up. So like the Neptunium series is what happens when neptunium decays, and you can doot. So you can see we go from neptunium to protactinium to uranium to thorium to radium to actinium to francium to astatine to bismuth, and then there's a bunch of different options there actually because it kind of splits, and eventually you get thallium. The protactinium is one of the top of these. I don't know that much about protactinium. It seems all right. I'm honestly going to put it in this kind of all right. But now we get to uranium. Uranium is just cool. And I don't think it's a hot take to say that uranium is dope. You can find it in nature. It's fluorescent. It glows. It makes these crazy. It makes these fluorescent stuff. We use it for nuclear energy. It's just really cool. And even in terms of actinide chemistry, I mentioned uranosine earlier. Like you can do chemistry with uranium. It's super cool. And like what? This is cyclooctatriene, right? So this is these octagons of carbon connected to your uranium atom. Like what even is this? This is so cool. You can do so much cool stuff with uranium and its fluorescent properties, and it's just awesome. Uranium is so cool. Delicious, yummy uranium. We love uranium. Uranium is absolutely S tier. All right. Neptunium. Really, the main thing about neptunium is that it's a decay product of americium. And this is one of the things where it's mostly just as a decay product. I don't know of any uses of neptunium directly. So we're putting it in D tier. Let me put that back up there. Get D tiered. Plutonium. Plutonium is also cool. I should mention another thing about these uranium these compounds is they're also often very chemically toxic. So one of the things with like americium, like smoke detectors, for example, is the radiation from it just there, on your wall or whatever is completely negligible. It's totally fine. If you were to somehow, for some godforsaken reason, inhale or like ingest the americium, then that would present a risk because you now have alpha radiation being blasted at your body, and alpha radiation is fine outside your body. Inside your body is very, very bad. But americium is also very, very chemically toxic. A lot of the actinides are also toxic just on a chemical level. And so people actually fight about like which would kill you first, right? Which is more, not even that, but which is more dangerous? Is it the chemical toxicity or the radiological toxicity? But yeah, so I should also mention that. Plutonium is, obviously used for nuclear stuff. It's kind of annoying, and it also forms compounds. The compounds that it forms are almost always pyrophoric too, which is incredibly dangerous and scary. A spontaneous plutonium fire is not something anyone wants to have. Plutonium is just kind of sucks, but it's whatever. We're putting it in C- tier. It's better. It at least has some kind of use. Americium is found in smoke detectors, where it's used to create alpha particles, and then you can smoke blocks those alpha particles so you can detect smoke. It's great. It's like an accessible radiation source. And what I did for the antimatter video, which is taking it out of the thing, is a terrible idea, and you should not do that. But what I did for the radiation shielding video, which is just like leaving it inside a smoke detector, and you just like using a smoke detector as a radiation source, it's like totally safe. It's accessible, and it's awesome, and they're really cool, and we love americium. Americium's A tier. Curium. I don't know much about curium. I feel like there's some tidbit that I was supposed to remember, but I completely forgot. So, yeah, good. Sorry, Curium, you're going here. Oh wow, there's a bunch more people here. Thorium is at least B tier. I mean, that's fair. The whole like reactor thing is pretty cool. Where did I put it? I don't even remember where I put it at this point. Thorium. Oh, I put it in D tier. What was I thinking? Did I forget about the whole reactor tiers? I'll put it in B tier. I think that's good. Hi, Micro, by the way. Why is Photoshop there? This is this is to represent exotic atoms. So the symbol PS is for positronium, which is like an atom, but instead of a positively charged nucleus, you have an antimatter electron, or a positron. And it kind of acts like a nucleus, right? Because you have a negatively charged thing and a positively charged thing. And there's a bunch of these. There's a bunch of exotic atoms. You can use muons. You can do all kinds of weird, bizarre stuff. And so this is, since PS is positronium, and I didn't want to mock up my own thing. We have the symbol PS right here. But I'll probably use it to represent just like all exotic atoms in general. And do you own uranium? :3. I mean, not right now. Do I want to own uranium? Yes. Will I hopefully own uranium at some point? Yes. Chlorine is a good leaving group. Yeah, exactly. Iodine is good because proiodic acid is yeah, I guess. Here, I love you, Tennessee, Sterling, Tennessee. Oh my gosh. Okay, we're not. Tsumi, there's another science VTuber named like Syzygy Altair, who for Valentine's Day who does like physics stuff, but for Valentine's Day is doing a Rizzix stream all about Riz. So like, you can pop in there if you want to tell them about your what you've created. Anyway, plutonium is cool because it's the neutron howitzer for the lab I was using. Yeah. So plutonium is useful for stuff. It has other uses that are not so great, but maybe we can promote it a little bit. I appreciate feedback. We can promote it to C tier. Like, on the one hand, a spontaneous plutonium fire is terrifying. But on the other hand, like, I don't know, it's kind of badass. We can put it in C tier. All right. We're getting to the home stretch now. All right. Berkelium. Berkelium I don't really know that much about. But the next one, californium, I do. I do know some things about californium. Californium is the isotope californium-252, which is a spontaneous neutron emitter. And there's a good picture that hopefully I can find. No, not that. There we go. So, inside this gigantic container is 1 gram of californium-252. This is because californium-252 doesn't emit normal like radiation. It's a neutron emitter. It spontaneously emits neutrons, which other stuff doesn't really do. Neutron radiation comes from nuclear reactors doing nuclear reactions, right? It's a byproduct of nuclear reactions, and it triggers more nuclear reactions and so on. And neutron radiation, californium-252 is basically the only case where we have something that's spontaneously emitting neutrons just as part of its decay, just by itself. And neutron radiation, as you might be able to tell from this ridiculous transport cask, neutron radiation is an absolute pain in the ass. So neutron radiation there's two main problems with it. First of all is that it's not really stopped by high atomic numbers. So like lead doesn't help that much more than anything else would. Instead, you basically just need a huge amount of concrete. You just need a ton of stuff for it to hit. The reason is because a positron, like atoms with high atomic numbers like lead and bismuth, have really big nuclei with a ton of protons. So you have a very, very, very positively charged nuclei that a proton will, interact with and deflect because it's such high positively charged. Whereas a neutron doesn't care. A neutron's, it's neutral by just like in the name. Right, so neutron radiation is an absolute pain to stop, but the thing that's even worse is what's called neutron activation. So if you have a neutron here, and let's say I have, some cobalt here, some ordinary cobalt, right? This is cobalt-59. Some ordinary cobalt that's just chilling as part of my reactor or whatever, and it gets hit with a neutron, it can turn the cobalt into cobalt-60. So we have activated the cobalt. And cobalt-60 is, of course, a very dangerous radioactive element. Again, I didn't mean dangerous is, depends on the quantity. But if you have enough of it, it can be very dangerous. And this is the worst radiation symbol ever drawn in the history of the world, but you get the idea. Neutron radiation can actually make other things radioactive. So it's the way you generally deal with this is a huge amount of basically water with something that can absorb neutrons. Something that does kind of like this process, but it doesn't turn into dangerous radioactive stuff. It turns into just another inert form. So you have to have some kind of something that can absorb neutrons. You usually have a ton of water, because the idea is that if you have basically, here's your big nucleus, right, which normally would help with stopping radiation, but neutron radiation really doesn't. If you have your big nucleus and we hit our tiny little neutron at it, it'll just bounce off and basically nothing happens. Or, so it's a kind of analogous to that. This is not exact physics, but it's roughly like that. Whereas if you have something really light, like let's say the hydrogen atoms in water, right? What can happen is the neutron is not that much heavier. So it can transfer some of its energy into the hydrogen atom, and it will now continue on with less energy, and you can slow it down. And this is called moderation. And it's really, really important, because what we're doing is we're slowing the neutrons down. And this is part of how nuclear reactors actually work in general, because you've probably heard the idea of you have a neutron coming in, or you have one neutron hits a nucleus. We'll pretend these diamonds are nuclei, and that releases a couple of neutrons, and then those neutrons go and hit nuclei, and now those produce more neutrons, and so on. You have this chain reaction, and yay, we have nuclear fission. But the trick here is that the production and the neutrons produced and the neutrons absorbed are not actually the same thing. So in this reaction, what's happening is you can only absorb neutrons that are slow, but you emit neutrons that are fast. So in order to have nuclear fusion, you don't just need to have uranium. You need to have something to slow this reaction down. You need to have a moderator, and water. Again, because the whole hydrogen atoms slow things down. Water's a very good moderator. There are other options you can do. The Germans tried heavy water, which turned out to be lame, and graphite works better, and there's all kinds of stuff to that. But the point is that neutron radiation is quite a pain, but this is basically the only way to just spontaneously make neutron radiation. And certain nuclear reactors actually need this, right? You need something to seed the process, right? You need something to seed, You need something to seed the process so that you can start doing nuclear fission. And so one of the uses of these californium-252 sources is as startup sources. So you have your nuclear reactor, but you need some neutrons to get it going. So you bring in temporarily a californium-252 source, and that creates your neutrons, starts up your nuclear reactor, and you're done with it. You don't need it anymore. So it's quite useful. And californium is really cool for that. So I'm going to put it in A tier. B tier, yeah, we're doing A tier. It's dope. It's a spontaneous neutron source. How cool is that? 99, we have Einsteinium, which, again, I don't know much about that one. And we're just in the actinide region. Then we have Fermium Mendelevium, Nobelium, Moscovium. Was I supposed to do Moscovium earlier? Oh well, it's still going in this area here. All right. Wait, I forgot to do phosphorus. Why am I so bad at this? Okay, well, phosphorus is trash. It's going in D tier. All right. It's time for the noble gases. We're ending on not just a high note, we are ending on a royal note. It is time for the noble gases. We begin with helium. Helium is, unfortunately, we're having a little bit of a renewability, sustainability problem with it, and we're running out of helium, but it is very, very useful. It's used, liquid helium is a very, very important cryogen. It gets you down to, I believe, about 4 Kelvin, and it's used for cooling everything from particle physics experiments to superconducting magnets for MRI machines use liquid helium. And it actually, so this is a bit of a side note, but liquid helium presents this in something like an MRI, MRIs are totally safe and fine, but if something does go wrong, you have this crazy, ridiculous scenario where here's your MRI or whatever, and it's in some room, right? You have an MRI in the scan room or whatever. If for some reason the MRI decides to randomly quench, so that is, quench just means release the liquid helium, right? So it's now releasing the liquid helium in the environment. That liquid helium will expand to a huge amount times its volume. So first of all, that presents a bit of like an asphyxiation hazard, right? Because that could displace oxygen. But the other thing is the pressure of this can like blow off doors and knock out, like it's just crazy what the pressure of all of this helium releasing can do. So again, they have to, real hospitals, it's safe to get an MRI. Real hospitals have measures in place to prevent this, but it's just this crazy thing that you wouldn't think of, right? If you're thinking about, what like in an MRI, you're just thinking about magnet, right? What could be dangerous? The magnet, and obviously, the magnet can be dangerous. But there's this not bizarre, but there's this risk or something that needs to be considered. Not really a risk, again. In modern systems, people have ways of accounting for this, but it's something that you wouldn't necessarily think of. Is if the MRI decides to quench and the cryogen is released, and the other thing is normally this vents like outside into a parking lot or something, right? But if the MRI decides to quench and the vent system fails, and you don't have a secondary vent system, then you have to deal with this cryogen being released into the MRI scan room and doing all kinds of ridiculous things. Like one of the things is one of the rules, I guess so to say, is that you're generally not allowed to have a inward swinging door to an MRI scan room, because what can happen is if the liquid helium expands, there's a huge amount of overpressure in the room that will lock the door shut. Right, you're now trapped in there, and asphyxiation could knock out their sight and stuff. It's the overpressure. Like this is, you can lose a ton of your senses too, because what happens is the overpressure can burst your eardrums, almost immediately, so you can't hear anything. There's this huge cloud of helium, so you can't see anything, and it's just this crazy scenario. And again, this is not really a risk in modern systems, but it's just interesting to think about it. It's not a risk you would think of. But anyway, that's a very, very tangential tangent about helium. But helium is obviously very important to astrophysics. Helium is very important as a cryogen. Helium, you can do even some chemistry with it, but it's just really great and cool. And we love helium. A tier, solid A tier. Then we get to neon. Neon, I think, is one of the most underrated elements, because everyone thinks neon is oh yeah, neon science. And this is true, it's cool. You can excite neon with a spark and it glows very brightly. Yay, neon science. But there's so much other stuff. Neon is actually the 5th most abundant element in the universe. It's much, much rarer than that on Earth, because it's so light, so it just goes, out into space. It doesn't hang around on Earth. But it's very, very common in the actual universe, which is kind of cool and weird. And also, the way neon was the first time that we discovered isotopes were even a thing, right? So we were talking about, obviously the whole idea of radioactivity and stuff depends on we have these different isotopes. You can have, potassium-40, which is radioactive, but there's other kinds of potassium that are not. Normal cobalt is cobalt, 59, but if you hit it with a neutron, you get cobalt-60. And all these different isotopes are discovery of the fact that these isotopes are a thing, came from finding 2 different isotopes of neon, using what was basically a mass spectrometer before mass spectrometers existed. It's crazy. So yeah, so that happened with neon, which automatically makes it really cool in my book. Neon is also used to form something called exomers. There's also helium-neon lasers, I should mention, which are another fun thing. Exomers are, actually, why am I going on Wikipedia? Whatever. The point is that an exomer is a case where you can have a molecule that only exists when one of the atoms is in an excited state, right? So if we have let's say we have, here's our A and here's our B, this cannot exist, right? This is not a stable compound that can exist. But if one of them is in an excited state, as long as it stays in that excited state, this bond actually can't exist, which is really cool. And neon can form a couple of those. So I don't know. I think neon's underrated and pretty great. I'm putting it in A tier. Not S tier, but A tier. Then we get to argon. Argon is very, very useful as a shield gas because it's more or less completely inert. And there are many inert gases, but argon is kind of the least annoying to use of these. Krypton is neon are super expensive. Oh, I forgot to mention actually, neon, according to current theory, is the most stable element too. So we haven't actually really gotten neon to form true compounds. We've been able to form some clathrates where it's sort of impregnated into ice. You can form exomers, and there are these things called van der Waals molecules, which are not really. I mean, it's kind of it's vaguely loosely bonded to it. But yeah, neon's theoretically at least the most stable element. Argon is also very stable. These are the noble gases, after all. Yeah, argon's very commonly used as a shield gas. I believe we have made some argon compounds, but of course that's very hard to do. Yeah, argon's really useful. There isn't that much to say about it other than its usage as an inert gas. So I think B tier. Krypton. Krypton, I think you can also form exomers with krypton, but I might be mistaken on that. Krypton has a really cool name. So it's basically argon, but more expensive, so it goes down, but has a cool name, so it goes up, so they're tied. Xenon. Oh boy. Xenon is an even cooler name. Xenon also is again a noble gas. You can form, it does react, right? So we have, if I mentioned PTF6, right? Platinum hexafluoride. You can use that to form xenon hexafluoride. There's other things too, though, where like xenon is used in xenon arc lamps. It's also a pretty potent, not asphyxiant. What's the word? It's an anesthetic. So xenon actually will like put you to sleep, and it's crazy. Like even though it's an inert gas, it diffuses into your like brain and can quite easily put you asleep. It's wild, and yeah, I don't know. Xenon's really cool. It gets, I think, A tier. All right, we're in the final stretch. Radon. Radon is kind of a pain.
Just we're closing in 10 minutes.
Yeah, so I'm getting kicked out soon, but that's okay. Superfluid helium-3. Oh, I didn't even think about. I forgot to mention helium can form a superfluid, which is when it's so cool. It basically kind of acts like a fluid with like no viscosity or like no friction. So paraffin is even better as a neutron moderator. Yeah. There's a bunch of different neutron moderators. Graphite was like one of the first ones that we found worked pretty well, but then we realized it's flammable and so it's not great. There's lots of alternatives. Neon signs, yeah. But yeah, superfluid helium-3 is basically, it acts like a fluid with no friction, kind of. And so what'll happen is if you put it in a glass, like a beaker or something, it will form like a incredibly thin layer on the side, and it will just flow out the sides anyway. Like it's ridiculous. Superfluids are awesome. But we were talking about radon. It's kind of more of just an annoyance, honestly. It's kind of just an annoyance. So I think it goes in D tier and oganesson. I mean, it's cool that it's the last element. Normally I would put it here with the other transactinides, but it is like the last one, right? That's cool. And now we're almost done. Which is good because I'm going to get kicked out of here too. We're almost done. What we have left is positronium, although really, again, it's representing all like exotic elements. So positronium is made from an electron and a positron, and this is like its symbol. Its symbol is PS. People have even made molecules with it. I believe someone has made positronium hydride, which is super weird and really cool. But there's other exotic atoms too. Like you can make muonic hydrogen, where you replace the electron with a particle called a muon. These exotic atoms are really cool. They absolutely go into S tier, and I think that's this. So I did say I was going to put a poll at the end for which ones should be, whether this S tier is truly deserving of S tier. So I think what I'll do is just put it, if you have any disagreements, if you would like to propose that one of the elements in S tier is undeserving of such a title, then say so in chat, and I'll put up a poll for it. We'll do it that way. But other than that, I think we've got our final. Until anyone questions one of the S tier elements, I think we've made our tier list in only like 4.5 hours. Amazing. I don't see any proposals. So does this mean this is the perfect tier list and I did everything perfectly? And I'll give it a little bit more time. In the meantime, I guess we can just review for it. So we have samarium. Samarium is really great and cool. We love samarium. I used it for the charity stream. I showed a lot of its cool properties. It's useful for organic reagents. It does all kinds of awesome stuff. Thulium, because it's element 69. Also, there's a cool paper I read where they used it to extract heavy metals from water. Iron kills stars. Come on. Gallium, like the whole liquid at room temperature thing, it has a really cool color when you put it under its spark. It's just awesome, and you can make gallium nitride and gallium arsenides for semiconductors. Great. On nihonium, I'm obligated to put this here as a weeb. Carbon is of course the backbone of organic chemistry. It's super important. Great. Silicon is the backbone of like the solid state sciences, and even ignoring that, even just in chemistry, like silane is cool. You can do all kinds of cool stuff with silicon. Bismuth is like lead, but kind of like lead, but actually non-toxic, and it's great and makes cool, pretty colors, and it's not straight, and it's just awesome. Sulfur goes into S tier partly because it does cool things and forms crazy allotropes, but also S tier. You get it. Fluorine is just wild. That is a thing that exists. I don't know if I mentioned it, but fluorine can literally set water on fire. Like it's insane. It's so cool. Uranium's just I mean, it's just so cool, right? You can, it's the backbone of the nuclear industry in our current present world, and probably will be for a very long time. It's just this accessible thing, and it's fluorescent and it glows, and it's so cool. And of course, exotic atoms are, in my opinion, really, really, really cool. Does nihonium need S? All right, I'll put it to a vote. I'll see if anyone agrees with me here. Is nihonium S tier? Yes, no. All right. We're finding it out. I mean, I had to put it there as, let's see this. I'm curious what people agree. It looks like we have 100% yeses. And that is one vote. Oh, no, it's 50-50. It's 50-50. Okay, wait, they changed their vote. Okay, we need someone to break the tie. Someone, break the tie. We need to know. Does nihonium belong in S tier? Is anime the way of the is this the way? Is this like the Mandalorian where this is the way? Or is this not the way? We need someone to break the tie. Otherwise, I'll break the tie. And I'll probably break it in favor of yes, but I would love not to have to do that. I love democracy. I want to see the answer. If you have any other things you would like to S tierify or question their status as S tier, feel free to put them forward. But I mean, look, 50-50, we can round up in favor of yes, right? I think that works. If you have any other little tidbits too that you want to share, feel free, whether they're related to how you're doing today or elements that you think I've underrepresented or something, or if there's just a cool story you want to share. It's up to you. Oh no. Okay, we're down to no. No is winning now. Okay, fine. Let's put it. What do we want to do? Let's put it in C- tier. Can we do that? Can we put it a little bit above D at least? I think we can do that, right? Up with its friends. Is that good? Oh, hi, Fairax. What do you think of our tier list? We finished it. We've made the tier list. Not finished it. We're still tweaking it. We're making sure it looks good. And then also, you can propose if you want to propose that any of the S tier elements are undeserving of their title. Then just say so in chat, and I'll put it to a poll. So, feel free to do that. But yeah, so I guess let's start with F tier and then work our way up. So in F tier, we have francium, which is toxic and does nothing and is stupid. Beryllium, which is toxic and does nothing and stupid. And tellurium, which is toxic and makes your breath permanently fucked and stupid. But is used to make solar panels. In D tier, we have barium, radium, scandium, promethium, dysprosium, ruthenium, hafnium, osmium, iridium, platinum, beryllium, copernicium, lawrencium, rutherfordium, dubnium, seaborgium, bohrium, hastnium, meitnerium, darmstadtium, thallium, fluorovium, arsenic, antimony, selenium, livermorium, polonium, chlorine, actinium, protactinium, neptunium, curium, berkelium, fermium, einsteinium, mendelevium, nobelium, moscovium, phosphorus, and radon. I feel like I'm doing the song, the periodic table song. And then in C tier, we have cesium, calcium, cerium, gadolinium, holmium, chromium, titanium, zirconium, niobium, molybdenum, rhodium, tantalum, rhenium, gold, aluminum, tin, astatine, nihonium, tennessine, and oganesson. I literally have this song running in my head and ended up timing it to the song. In C tier, we have sodium, strontium, lanthanum, praseodymium, europium, manganese, zinc, palladium, cadmium, tungsten, indium, lead, iodine, and plutonium. In B tier, we have potassium, magnesium, neodymium. I'll just do it again. Potassium, magnesium, neodymium, terbium, erbium, ytterbium, cobalt, nickel, technetium, silver, mercury, thorium, argon, krypton. And then in A tier, these are the really great ones. We have hydrogen, lithium, rubidium, yttrium, lutetium, vanadium, copper, boron, germanium, nitrogen, oxygen, bromine, americium, californium, helium, neon, xenon. Neon, xenon. There we go. And pretty cool. That's why I joined, despite it being 6:29 a.m. here. Oh no. I feel you, honestly. My sleep schedule is far gone at this point. Far gone. Yeah. And then we have our amazing epic S tier elements of samarium, the element that does cool magnetic stuff, and I have a special attachment to because my first live stream was about it. Thulium, element 69. Iron, the star killer, the star destroyer, like Star Wars. It's the Star Destroyer. It's so perfect. Gallium, which is almost a liquid metal at room temperature and is used for dope semiconductor stuff. Carbon is backbone of organic chemistry. Silicon is all the chips and stuff. Bismuth makes cool colors and is like lead but better and also not straight. Sulfur makes a bunch of allotropes, and S is S tier. It's perfect. Fluorine is just wild and can oxidize oxygen. Come on, oxidizing oxygen. Like what? What? How is this a thing? How is this a thing? How is this a thing? Can I even spell it? No. That's how much of not a thing it is. It's so much of not a thing that I can barely spell it. It's so much of not a thing, but it's still a thing because fluorine is dope. What? You can oxidize oxygen? I know, okay. And uranium. I really need to explain how awesome uranium. Come on, it's uranium. It's radioactive, and you can find it in rocks and stuff, and it glows and shit. And positronium here. We have positronium representing our exotic atoms. Positronium specifically being antimatter electron and matter electron, forming something analogous to an atom. But if that's all that is, I think we have to make one final poll of, is this the correct, perfect tier list with no flaws or errors whatsoever? Let's see what people think of this. Because I think this is pretty good, honestly. I like the way this is. Mercury it's really cool, but it's toxic, so it gets dropped down a little bit. Why did I put? Oh yeah, vanadium is dope just in general because you can do flow batteries and it makes all the different pretty colors and this is really chemically cool. But also V for VTubers, come on. Lutetium I'm a little on the fence about putting it in A tier. Should I drop it down? The whole idea of you have a radiation detector made with lutetium. And so your radiation detector is itself radioactive, and so you can calibrate shit. That's really cool. That's cool. I think that's A tier material. Nickel, technetium. Technetium's cool. I'm pretty happy with this, honestly. It's almost like I made it or something. W take, I guess. Phosphorus should be higher. That's fair. Where did I put phosphorus? It is. We can put it in C- tier. I think we can promote phosphorus. I feel comfortable promoting phosphorus. Let's do that. I'll put it here though to make it in order-ish, even though it's totally not in order. But I think that's what we got. I'm leaving it. But the yes is winning in the poll, so I think I'm just going to end the poll here, and I think that's what we got. Phosphorus has been promoted. I think everything's physically perfectly perfect now. So this is where I guess I hit the end stream button. Thank you all so much for coming out, especially with this awkward part 2 situation that wasn't really, this was just an hour break. Thank you all so much for coming to this stream. And I'm getting kicked out now, so bye!